The Big Bang itself. What do we actually mean by the beginning? When you close your eyes and think about the Big Bang, what image comes to mind? Perhaps you imagine a massive explosion, like a cosmic firework bursting in the darkness of space, sending matter flying outward in all directions. This is the picture that most of us carry, shaped by countless documentaries, books, and casual conversations about the origin of our universe. But here's something that might surprise you as you drift off tonight. That mental image, as vivid and compelling as it is, isn't quite right. The Big Bang wasn't an explosion in space at all. It was something far stranger, far more profound, and in many ways, far more beautiful. Let's take a gentle journey together through one of the most fascinating stories science has ever uncovered. As you relax and let your mind wander, we'll explore what we really mean when we talk about the beginning of everything, and discover why this question leads us to the very edge of human knowledge. First, let's address that stubborn misconception about the explosion. When we hear the word bang, we naturally think of something blowing up, like a firecracker on a summer night, or a balloon popping at a birthday party. In these familiar events, there's always a center point where the explosion happens, and debris flies outward into the surrounding space. There's an inside and an outside, a here and a there. But the Big Bang was fundamentally different from anything we experience in our everyday lives. The Big Bang wasn't an explosion of matter into empty space. Instead, it was the expansion of space itself. Imagine for a moment that the entire universe, everything that exists, is like the surface of a balloon. Now picture that balloon being inflated. As it grows, every point on the surface moves away from every other point. But there's no single spot that's the center of the expansion. If you were an ant living on that balloon surface, you'd see all your ant neighbors moving away from you, and each of them would see exactly the same thing from their perspective. No one is at the center because the surface itself is what's expanding. This is closer to what the Big Bang was like, except even this analogy has limitations. The universe isn't expanding into anything because there is no outside. Space itself came into being with the Big Bang, and time did too. Before the Big Bang, well, there was no before in any sense we can meaningfully talk about, because time itself hadn't started yet. Take a moment to let that settle in your mind. It's a strange thought, isn't it? We're so accustomed to thinking of time as an endless river, flowing from the infinite past toward the infinite future. But what science suggests is that time has a beginning, a first moment, before which the very concept of before makes no sense. It's like asking what's north of the North Pole. The question seems meaningful, but when you really think about it, it dissolves into confusion because you've reached the edge of where that concept applies. Now, when physicists talk about the Big Bang, they're describing a state where the universe was incredibly hot, incredibly dense, and incredibly small. But how small are we talking about? This is where things become almost dreamlike in their strangeness. If we could somehow rewind cosmic history, watching galaxies rush back together, stars dissolve, atoms break apart, we'd eventually reach a point where the entire observable universe, everything we can see with our most powerful telescopes, all the billions of galaxies containing trillions of stars, would be compressed into a space smaller than a single atom, smaller than an electron, smaller than anything we have words for. This incredibly compact, incredibly hot state is sometimes described as a singularity, a point where the density and temperature become infinite, or at least where our mathematical descriptions tell us they should become infinite. But here's where we need to pause and acknowledge something important. This singularity is more of a signpost indicating the limits of our knowledge than it is a real physical thing we understand. Think of it this way. Imagine you're following a map through a forest, and the path leads you to the edge of the map where it simply says, "Here be dragons." That's not because there are literally dragons there. It's because the map maker didn't know what was beyond that point. The singularity is our cosmological version of "Here be dragons." It's where our current physics breaks down and stops giving us reliable answers. Why does this happen? Why do our equations and theories fail us at this crucial moment? The answer lies in a fundamental tension at the heart of modern physics, a story of two extraordinarily successful but seemingly incompatible theories. On one side, we have general relativity, Einstein's beautiful geometric theory of gravity. This is the framework we use to understand the large-scale structure of the universe, the behavior of massive objects like stars and galaxies, the warping of space and time. General relativity has passed every experimental test we've thrown at it with flying colors. It predicted black holes, gravitational waves, the expansion of the universe itself. On the other side, we have quantum mechanics, the theory that governs the microscopic world of atoms and subatomic particles. Quantum mechanics is equally successful in its domain, explaining the behavior of matter and energy at the smallest scales, giving us transistors and lasers and all the technology of the modern world. But here's the problem that keeps physicists awake at night. These two theories don't play nicely together. When we try to apply both of them to the same situation, especially situations involving extremely high energy in extremely small spaces, the equations break down. They give us nonsensical answers, infinities that shouldn't be there, predictions that make no sense. The earliest moment of the universe is precisely such a situation. Space is compressed to quantum scales, but the gravity is enormously strong. We need both quantum mechanics and general relativity to describe what's happening, but we don't have a theory that successfully combines them. This missing theory, this holy grail of theoretical physics, is what scientists call quantum gravity. Until we have a working theory of quantum gravity, there's a wall beyond which we cannot see, a moment in cosmic history before which our understanding becomes speculation. This moment has a name: the Planck epoch. The Planck epoch is the earliest period in the history of the universe that we can even begin to discuss with our current physics. It lasted from time 0 to approximately 10 to the power of minus 43 seconds after the Big Bang. Let's take a moment to appreciate just how incomprehensibly brief this is. 1 second can be divided into 1,000 milliseconds. Each millisecond can be divided into 1,000 microseconds. Each microsecond into 1,000 nanoseconds, each nanosecond into 1,000 picoseconds, each picosecond into 1,000 femtoseconds, each femtosecond into 1,000 attoseconds, each attosecond into 1,000 zeptoseconds, each zeptosecond into 1,000 yoctoseconds. And we're still nowhere close. We need to go about 20 orders of magnitude smaller still to reach the Planck time, the duration of the Planck epoch. This unimaginably tiny sliver of time is named after Max Planck, one of the founders of quantum mechanics. He discovered that there are fundamental units built into the fabric of nature, minimum meaningful quantities below which our usual notions of measurement break down. The Planck time is one of these fundamental units. During this first moment, the universe was smaller than 10 to the power of minus 35 meters across. That's the Planck length, another fundamental unit. To put this in perspective, if we expanded an atom to the size of the observable universe, the Planck length would still be about the size of an average tree. It's not just small, it's cosmically, absurdly, fundamentally small. What was happening during this Planck epoch? The honest answer is, we don't know. The universe was so hot, so dense, so extreme, that quantum effects and gravitational effects were equally important, and our physics can't handle that combination. Space and time themselves might have been boiling and fluctuating in ways we can barely imagine. Some theories suggest that time might not even have been a single linear dimension, but something more complex, something that would make our usual understanding of cause and effect meaningless. This might sound frustrating. After all, we're trying to understand the beginning of everything, and we're immediately confronted with a barrier we can't see past. But there's something almost poetic about this limitation. The universe itself seems to have a veil drawn across its earliest moments, a natural horizon beyond which our current understanding cannot reach. What comes after the Planck epoch, however, we understand much better. As the universe aged beyond this first incomprehensibly brief instant, it entered regimes where our physics works wonderfully well. The universe expanded and cooled, particles formed, forces separated from each other, matter and antimatter annihilated, leaving behind the slight excess of matter that would eventually become everything we see. The universe became transparent to light. Stars formed, galaxies gathered, and here we are, 13.8 billion years later, looking back and trying to piece together how it all began. The fact that we can't peer directly into the Planck epoch doesn't mean scientists have given up on understanding it. Far from it. Around the world, theoretical physicists are working on various approaches to quantum gravity. Some are pursuing string theory, which suggests that the fundamental constituents of reality aren't particles but tiny vibrating strings, and that space might have extra dimensions we can't directly perceive. Others are exploring loop quantum gravity, which suggests that space itself is made of discrete chunks, quantum atoms of volume. Still others are investigating different approaches, each with its own mathematics and predictions. These theories are incredibly difficult to test because the energies required to probe the Planck scale are far beyond anything we can produce. In our particle accelerators, even the mighty Large Hadron Collider, we can't build a microscope powerful enough to see the fabric of space at this level. But physicists are clever, and they're finding indirect ways to test these ideas. They look for subtle imprints on the cosmic microwave background, the afterglow of the Big Bang that fills the sky. They study the behavior of black holes, where similar extreme conditions exist. They search for subtle violations of symmetries that might hint at the quantum structure of space-time. As you lie here in the quiet darkness, consider the remarkable fact that we can talk about these things at all. For most of human history, the origin of the universe was purely a matter of mythology and speculation. Different cultures told different stories, some involving cosmic eggs, some featuring battles between gods, some describing cyclical creation and destruction. These stories were humanity's attempts to make sense of the profound mystery of existence. What changed is that we developed a new tool, the scientific method. We learned to observe nature carefully, to propose explanations that could be tested, to build mathematical models that make predictions, and to refine or discard those models based on experimental evidence. This approach has taken us from complete ignorance about the nature and origin of the universe to a remarkably detailed understanding, even if that understanding has clear boundaries. The Big Bang Theory isn't just speculation or guesswork. It's supported by multiple independent lines of evidence. We see galaxies moving away from us in all directions, exactly as we'd expect if space itself is expanding. We detect the cosmic microwave background, the cooled remnant of the hot early universe, with exactly the properties the theory predicts. We observe the abundances of light elements like hydrogen and helium, which match the predictions of Big Bang nucleosynthesis, the process by which the first atomic nuclei formed in the first few minutes after the Big Bang. All of this evidence points to the same conclusion. The universe had a beginning, a moment when space and time came into existence in a hot, dense state and began expanding and cooling. This is one of the most profound discoveries in the history of human thought, ranking alongside the realization that the Earth orbits the Sun, or that life evolved over billions of years through natural selection. But the discovery comes packaged with humility. We know the story back to a certain point, and then we reach a horizon beyond which we cannot currently see. This horizon isn't arbitrary or accidental. It's baked into the nature of reality as we understand it. To see beyond it, we need to understand how gravity behaves in the quantum realm, and that's a puzzle we haven't yet solved. Some people find this frustrating or unsatisfying. They want complete answers, total certainty. But there's another way to look at it. The existence of this horizon, this ultimate frontier of knowledge, is what makes cosmology exciting. It means there are still deep mysteries to solve, fundamental questions to answer. It means future generations will have the thrill of discovery, the joy of pushing back the boundaries of human understanding. And perhaps the very existence of this limit teaches us something important about knowledge itself. There may always be questions at the edge of what we can know, mysteries that beckon us forward. This doesn't mean we should stop asking questions, or that all answers are equally valid. It means that the universe is genuinely mysterious in ways we can precisely define and think about rigorously. As you drift towards sleep tonight, you might find comfort in this thought. You live in a universe that's comprehensible enough to be understood, but mysterious enough to be endlessly fascinating. We know so much about the cosmos, from the formation of galaxies to the fusion of elements in stellar cores, to the expansion of space itself. And yet, the deepest question of all, the question of the absolute beginning, still awaits a complete answer. The Big Bang wasn't an explosion in space. It was the beginning of space, the beginning of time, the beginning of everything. It happened everywhere at once because everywhere was compressed into a volume smaller than you can imagine. It happened in no particular place because place itself came into being with it. And the very first moment, that incomprehensibly brief Planck epoch, remains shrouded in mystery, waiting for a future theory to illuminate it. Until then, we stand at the shore of cosmic time, looking back across billions of years of cosmic history that we can map and understand, knowing that beyond a certain point, there's a horizon we haven't yet learned to see past. And that's okay. That's part of the grandeur of the scientific enterprise, the humility and ambition combined, the willingness to say both what we know and what we don't know. As you close your eyes and let sleep come, remember, you are made of atoms forged in stars that formed from gas clouds, that condensed from density fluctuations, that originated in the first moments after the Big Bang. You are the universe trying to understand itself, a collection of particles arranged in such a way that you can contemplate your own origins. And those origins, mysterious as they partly remain, are more wonderful than any story our ancestors invented. The beginning of everything wasn't just a bang. It was the beginning of space, time, matter, energy, and ultimately, consciousness. It was the start of a story that includes you, here, now, thinking about it all. And that's something worth resting peacefully with. The first picosecond. How did the fundamental forces emerge? Imagine you could witness the first picosecond of the universe's existence. A picosecond is 1/1,000,000th of a second, a span of time so brief that light, traveling at its ultimate cosmic speed limit, would barely cross the width of a human hair. Yet within this impossibly short moment, the universe transformed itself in ways more dramatic than all the billions of years that would follow. Forces separated, space itself erupted into exponential growth. The seeds of every galaxy, every star, every planet, and every living thing were planted. And most mysteriously of all, a tiny imbalance between matter and antimatter ensured that you and I would someday exist to contemplate it all. As you settle into rest tonight, let's explore these first fleeting instants when the universe's fundamental character was established, when the rules that would govern all future cosmic evolution were written into the fabric of reality itself. We've already established that we can't see directly into the Planck epoch, that first 10 to the power of -43 seconds. But as the universe aged beyond this initial quantum fog, it entered a phase we can describe with more confidence. This is where our journey through the first picosecond truly begins, in a period called the Grand Unification Epoch. The Grand Unification Epoch lasted from roughly 10 to the power of -43 seconds to about 10 to the power of -36 seconds after the Big Bang. To appreciate what made this epoch grand, we need to understand something about the forces that govern our universe today. In our present-day universe, we experience 4 fundamental forces. There's gravity, which keeps your feet on the ground and holds planets in orbit around stars. There's electromagnetism, which governs everything from the light you see to the chemical bonds that hold your body together. There's the strong nuclear force, which binds quarks together into protons and neutrons and holds atomic nuclei together despite the electromagnetic repulsion between protons. And there's the weak nuclear force, which governs certain types of radioactive decay and plays a crucial role in how stars shine. These 4 forces seem quite different from each other in the world we inhabit. Gravity is by far the weakest, yet it operates over infinite distances. Electromagnetism is much stronger and also acts over long ranges. The strong force is powerful, but only works over distances smaller than an atomic nucleus. The weak force is, as its name suggests, weak and operates over even shorter ranges than the strong force. But physicists have discovered something remarkable. These forces aren't as different as they appear. As you increase the energy, as you probe smaller distances or recreate the conditions of the early universe, these forces begin to show their kinship. They start to behave more similarly. They merge together. We've already seen this happen once in our experiments. At energies we can achieve in particle accelerators, we've confirmed that electromagnetism and the weak nuclear force are actually 2 aspects of a single force, the electroweak force. Below a certain energy threshold, this unified force splits into the 2 separate forces we observe today. But at high enough energies, they're revealed to be one. The Grand Unification Epoch was a period when the universe was so hot, so energetic, that the strong nuclear force and the electroweak force were unified into a single grand unified force. During this time, there were only 2 forces in the universe, gravity and this grand unified force. The universe was simpler then, more symmetric, more elegant. Picture the universe during this epoch. Its temperature was around 10 to the power of 28 degrees. That's 10 followed by 28 zeros degrees. There's no meaningful way to relate this to everyday experience. The core of the Sun, where nuclear fusion occurs, is a mere 15 million degrees. The hottest things we've ever created in particle colliders reach a few trillion degrees. The Grand Unification Epoch was more than a trillion times hotter still. At these temperatures, matter as we know it couldn't exist. There were no atoms, no nuclei, not even stable protons or neutrons. Instead, the universe was filled with a roiling soup of fundamental particles and their antiparticles, constantly being created and destroyed as energy converted to matter and back again. Quarks, leptons, gauge bosons, all swimming in this primordial plasma, all interacting through the grand unified force and gravity. But the universe was expanding, and as it expanded, it cooled. This is one of the most important principles of cosmology. Expansion equals cooling. It's similar to what happens when you release compressed air from a tire or a spray can. The gas expands and gets colder. But the cosmic expansion was far more dramatic, and the cooling far more consequential. As the temperature dropped through this epoch, the universe was approaching a critical threshold. Just as water freezes into ice when it cools below 0 degrees Celsius, or water vapor condenses into liquid when it cools below 100 degrees, the unified force field pervading the universe was about to undergo what physicists call a phase transition. Around 10 to the power of minus 36 seconds after the Big Bang, when the universe had cooled to a mere 10 to the power of 27 degrees, something extraordinary happened. The grand unified symmetry broke. The strong nuclear force separated from the electroweak force, becoming distinct. The universe became more complex, less symmetric. But in doing so, it took on characteristics that would eventually allow structure and life to emerge. This phase transition released enormous amounts of energy, like water releasing heat when it freezes into ice. And this energy drove the most dramatic event in cosmic history: inflation. Cosmic inflation is one of the most remarkable ideas in all of science. Proposed in the 1980s by physicist Alan Guth and refined by many others since, inflation suggests that the universe underwent a brief period of exponential expansion, growing faster than the speed of light. Now wait, you might think, doesn't relativity tell us that nothing can travel faster than light? That's true, but there's a subtle point here. While matter and energy can't move through space faster than light, space itself has no such speed limit. During inflation, space was expanding so rapidly that distant regions were rushing apart faster than light could travel between them. How rapid are we talking? In a period lasting perhaps 10 to the power of minus 32 seconds, the universe expanded by a factor of at least 10 to the power of 26. That's 100 million trillion times larger. A region smaller than a single atom expanded to something the size of a grapefruit or larger. And this all happened in a time span that makes a blink of an eye seem like an eternity. To help you visualize this as you drift towards sleep, imagine you're holding a balloon with a few specks of dust on its surface. Those specks represent different regions of space. Now imagine inflating that balloon, but instead of it growing, at a normal pace, it suddenly explodes outwards so fast that the specks, which were close enough to see each other, are now separated by distances so vast that light would need more than the current age of the universe to travel between them. That's inflation. This might sound like wild speculation, but inflation solves several profound puzzles about the universe we observe. Let's explore two of the most important: the horizon problem and the flatness problem. The horizon problem is this. When we look at the cosmic microwave background, that afterglow of the Big Bang filling the sky, we see that it has almost exactly the same temperature in every direction. The difference between the hottest and coldest spots is only about 1 part in 100,000. This uniformity is remarkable, but it's also puzzling. For regions of space to have the same temperature, they need to have been in contact at some point, able to exchange energy and reach equilibrium. Like how hot coffee in a cup eventually reaches a uniform temperature throughout. But according to the standard Big Bang model without inflation, Many regions of the observable universe were never in contact. They're separated by distances so vast that light hasn't had time to travel between them, even in the entire age of the universe. So how did they all end up at the same temperature? It's as if you found that 2 cups of coffee on opposite sides of the universe, which had never interacted, were at exactly the same temperature. It seems impossibly coincidental. Inflation solves this elegantly. Before inflation, the entire observable universe was compressed into a region tiny enough that all its parts were in contact, able to reach equilibrium. Then inflation stretched this small uniform patch to enormous size. That's why the cosmic microwave background looks so uniform. We're seeing different parts of what was once a small, thermally connected region. The flatness problem is equally intriguing. Space, according to general relativity, can be curved. It can bend like the surface of a sphere or saddle. The curvature depends on the total density of energy in the universe. If the density is too high, space curves back on itself like a sphere. If it's too low, space curves outward like a saddle. But observations tell us that space is remarkably flat, or very nearly so, meaning the density is almost exactly at the critical value between these extremes. Here's the puzzle. The early universe didn't have to be flat. It could have had any curvature. But as the universe evolves, any initial curvature gets amplified. If the early universe was even slightly curved, it would have become extremely curved by now, either collapsing back on itself or expanding so fast that no structures could form. For the universe to be as flat as we observe it today, the initial conditions had to be fine-tuned to an absurd degree, accurate to 1 part in 10 to the power of 60 or more. That level of precision seems bizarre and unexplained. Inflation solves this too. When space undergoes exponential expansion, any initial curvature gets stretched out, flattened, like how the surface of a balloon appears flatter and flatter as you inflate it. If you blow up a balloon to the size of the Earth, its surface would look perfectly flat to anyone standing on it. Inflate space by a factor of 10 to the power of 26 or more, and any initial curvature becomes undetectable. So inflation wasn't just a dramatic event. It was a necessary process that explains fundamental features of the universe we observe. The seeds of cosmic structure, the density fluctuations that would eventually grow into galaxies, were quantum fluctuations stretched to cosmic size by inflation. The uniformity of the universe, the flatness of space, the very fact that we can see a smooth cosmos in every direction, all trace back to this brief moment of exponential growth. But inflation and the separation of forces weren't the only crucial events in this first picosecond. Something else happened, something even more mysterious, something that ensured you would exist to hear this story. This was baryogenesis, the creation of the matter-antimatter asymmetry. To understand baryogenesis, we need to talk about antimatter. For every type of particle in nature, there exists an antiparticle with the same mass but opposite charge. The antiparticle of an electron is a positron, identical in mass but positively charged instead of negatively charged. The antiparticle of a proton is an antiproton, with negative charge instead of positive. When a particle meets its antiparticle, they annihilate each other, converting their mass entirely into energy in a flash of light. In the hot, early universe, particles and antiparticles were constantly being created in equal numbers from pure energy and then annihilating back into energy. This is what quantum field theory predicts. At high enough temperatures, the vacuum itself is boiling with particle-antiparticle pairs popping into and out of existence. Here's the puzzle. The physics we understand suggests that particles and antiparticles should be created in exactly equal numbers. The laws of physics, as we know them, treat matter and antimatter almost identically. So as the universe cooled, all the matter should have annihilated with all the antimatter, leaving behind a universe filled only with light, with photons carrying the energy that had been locked in matter and antimatter. But that's not what happened. Obviously, you exist. And you're made of matter, not antimatter. The stars are made of matter. The galaxies are made of matter. When we look out into the cosmos, we see no evidence of significant amounts of antimatter anywhere. The universe is overwhelmingly matter-dominated. This means that somehow, in those early moments, a tiny excess of matter over antimatter was created. For every billion antiparticles, there were 1,000,000,001 particles. When all the annihilation was done, when every antiparticle had found a particle partner and vanished in a burst of energy, that one in a billion excess remained, and that leftover, that cosmic remainder, is everything we see. Every atom in your body, every star in the sky, every planet, every galaxy. The process that created this asymmetry is called baryogenesis. Baryons are particles like protons and neutrons made of 3 quarks, and they're the main constituents of ordinary matter. So baryogenesis means the genesis, the creation, of the excess of baryons over antibaryons. How did this happen? The honest answer is we're not entirely sure. We know it must have happened because we exist, and we know, thanks to physicist Andrei Sakharov, what conditions are necessary for it to occur. Sakharov identified 3 requirements. First, there must be processes that violate baryon number conservation, meaning reactions that can change the total number of baryons. In most interactions we observe today, baryon number is conserved, but in the extreme conditions of the early universe, at the grand unification energy scale, such violations might occur. Second, there must be violation of what's called charge conjugation symmetry and a related symmetry called CP symmetry. In simple terms, the laws of physics must treat matter and antimatter slightly differently, not exactly the same. We've observed such violations in certain weak interactions, but not at a level that seems sufficient to explain the observed matter-antimatter asymmetry. Third, these processes must occur out of thermal equilibrium. If the universe is in perfect equilibrium, any asymmetry that gets created will be washed out. But during phase transitions, like the breaking of the grand unified symmetry, the universe can temporarily fall out of equilibrium, providing a window for asymmetry to develop and persist. All 3 of Sakharov's conditions can be met in the early universe, particularly during the grand unification epoch and the moments following. Various theories propose different mechanisms for baryogenesis. Some involve the decay of hypothetical heavy particles called X bosons, which would have existed when the grand unified force was still unified. These bosons might have decayed slightly more often into quarks than into antiquarks, creating the asymmetry. Other theories connect baryogenesis to the physics of neutrinos, those ghostly particles that barely interact with anything. If neutrinos have certain properties, if they're their own antiparticles and have mass, then processes called leptogenesis could create an excess of leptons, which would then be partially converted into an excess of baryons through other interactions. The truth is, we don't yet know exactly which mechanism is responsible. Baryogenesis remains one of the great unsolved mysteries of cosmology and particle physics. It connects to deep questions about the nature of matter, the unification of forces, and physics beyond what we've been able to test experimentally. As you lie here in the darkness, let this thought settle gently in your mind. Your existence depends on a 1 in a billion cosmic accident, an asymmetry that emerged in the first microseconds of time. If matter and antimatter had been created in exactly equal amounts, if that tiny imbalance hadn't emerged, the universe would be filled with nothing but light. No atoms, no chemistry, no stars, no planets, no life, no consciousness. Just photons racing through empty space forever. But the imbalance did occur, and when the universe had cooled enough, after about 1 microsecond, the remaining quarks bound together into protons and neutrons. After a few minutes, those protons and neutrons fused into the first atomic nuclei. After a few 100,000 years, electrons joined nuclei to form the first atoms. And hundreds of millions of years later, those atoms gathered into clouds that collapsed into the first stars. All of this, the entire rich tapestry of cosmic structure and evolution, traces back to those first moments, that first picosecond when forces separated, when space inflated to vast size, when a mysterious asymmetry ensured that matter would survive. The universe during that first picosecond was a place utterly unlike anything in our experience, hotter than we can truly imagine, denser than we can picture, evolving faster than we can comprehend. The fundamental forces were unifying and separating. Space itself was stretching exponentially. Particles and antiparticles were appearing and annihilating in a cosmic dance. And somehow, through processes we're still working to understand, the stage was set for everything that would follow. There's something almost musical about it all. A cosmic symphony playing itself out at impossible speeds. The universe was finding its form, its structure, its character. The laws of physics were manifesting themselves. Symmetries were breaking. Forces were differentiating. In that brief moment, shorter than any human thought, longer than any we can truly grasp, the universe transformed from primordial simplicity to structured complexity. As you drift into sleep tonight, you might find wonder in this. The atoms in your body, forged in stars, are made of particles that survived the Great Annihilation because of a 1 in a billion asymmetry. Those particles exist in their current forms because the strong force separated from the electroweak force in a phase transition that happened in less time than light takes to cross an atom. The uniformity of the universe around you, the fact that physical laws are the same everywhere, traces back to a period of exponential expansion that lasted a tiny fraction of a second. The first picosecond set everything in motion. It determined the large-scale structure of the cosmos. It ensured that matter would dominate over antimatter. It planted the seeds that would grow into galaxies. All of cosmic history, all 13.8 billion years from then until now, has been in some sense an unfolding of what was established in that brief instant. And we, improbable collections of matter, arrangements of atoms complex enough to ponder their own origins, can look back across the vast sweep of time and reconstruct this story. We can calculate what conditions must have been like. We can predict what should have happened. We can test those predictions against observations of the cosmos. And piece by piece, we can recover the narrative of those first moments. There's still much we don't understand. The exact mechanism of baryogenesis remains mysterious. The physics of the grand unified force remains hypothetical, beyond the reach of our experiments. The precise details of inflation, what drove it and how exactly it began and ended, are still debated. But the broad outline is clear, supported by multiple lines of evidence. As your breathing slows and sleep approaches, rest easy with this knowledge. You are the descendant of that first picosecond, the inheritor of its asymmetries and its patterns. The forces that govern your atoms separated then. The matter you're made of survived then. The structure of the cosmos was established then. In the briefest flash of cosmic time, everything was decided. And now, billions of years later, on a small planet orbiting an ordinary star in an unremarkable galaxy, you can close your eyes and understand, at least in broad strokes, what happened in that inconceivable moment. You can know your cosmic origins. You can trace your lineage back not just to ancient ancestors or primordial seas, but to the first picosecond of time itself, when the universe was young and hot and simple, and everything was beginning. The quark gluon plasma. What was the universe's primordial? Soup, close your eyes and imagine a soup. Not an ordinary soup, but the most primordial soup imaginable. A cosmic broth that existed before there were atoms, before there were even the building blocks of atoms as we know them today. This wasn't chicken noodle or vegetable stew. This was a seething ocean of the most fundamental particles known to physics, moving freely in a state of matter so exotic that it vanished from the universe almost as quickly as it appeared, and wouldn't be seen again until humans learned to recreate tiny droplets of it in the most powerful particle colliders on Earth. As you settle into rest tonight, let's explore this primordial state of matter. This quark gluon plasma that filled the infant universe after inflation ended, and before the familiar particles we know today came into being. It's a story of transformation, of how the universe cooled from an undifferentiated soup into structured matter, how the ingredients of everything you see around you emerged from chaos into order. After the dramatic burst of inflation, after space had expanded exponentially and the universe had undergone its violent growth spurt, things began to settle into a slightly more sedate rhythm. Slightly more sedate, but still almost incomprehensibly extreme. The universe was still unimaginably hot, still incredibly dense, still filled with energy that would make the core of any star seem cold and empty by comparison. We're now in the period from about 10 to the power of minus 12 seconds to about 10 to the power of minus 6 seconds after the Big Bang. That's from 1/1,000,000,000 of a second to 1/1,000,000th of a second. This period is sometimes called the quark epoch, and during this time, the universe existed in a state that physicists call quark gluon plasma. To understand what this means, we need to take a step back and talk about what matter is made of at its most fundamental level. You've probably learned that everything around you is made of atoms. Atoms have a nucleus made of protons and neutrons, surrounded by a cloud of electrons. This is the picture we carry from school, and it's correct as far as it goes. But it's not the whole story. Protons and neutrons aren't actually fundamental particles. They're made of something smaller, something more basic. Each proton is made of 3 quarks, specifically 2 up quarks and 1 down quark. Each neutron is also made of 3 quarks, but with a different combination. 2 down quarks and 1 up quark. These quarks are held together by particles called gluons, and the force that binds them is the strong nuclear force, the strongest of all the fundamental forces in nature. In the world we inhabit today, you never see a quark by itself. They're always bound together in groups, confined inside protons, neutrons, and other similar particles. This confinement is absolute. You cannot pull a quark out of a proton no matter how hard you try. If you put enough energy into trying to separate quarks, you don't free them. Instead, you create new quark-antiquark pairs from that energy, and they immediately bind together into new particles. It's as if quarks have an unbreakable agreement never to be alone, always to be bound to partners. But in the earliest moments of the universe, things were different. The universe was so hot, the energy was so intense, that quarks and gluons moved freely, unconfined, like individual ingredients floating in a soup, before they've had time to combine into anything recognizable. This free-flowing state of matter is the quark-gluon plasma. Imagine standing at a stove, watching a pot of water. At room temperature, water molecules are bound together by hydrogen bonds, forming a liquid with structure and viscosity. But heat that water to boiling, and those bonds break. The water turns to steam, and the molecules move freely, independently. The quark-gluon plasma is something like this, but instead of water molecules breaking free from each other, it's the components of protons and neutrons themselves, the quarks and gluons, that are unbound and moving independently. The temperature during the quark epoch was somewhere around 10 trillion degrees, about 1,000,000 times hotter than the core of the sun. At these temperatures, the universe was a roiling sea of fundamental particles, quarks of different types, or flavors as physicists call them, up quarks, down quarks, strange quarks, all moving at nearly the speed of light. Gluons, the force-carrying particles of the strong interaction, constantly being exchanged between quarks. Electrons and their heavier cousins, muons and tau particles, along with neutrinos of various types. Photons, the particles of light, and all of their antiparticles too, present in nearly equal numbers. This plasma wasn't like any liquid or gas you've ever encountered. It was a state of matter so hot and dense that our usual distinctions between particles break down. The quarks weren't individual objects bouncing around like balls in a box. They were quantum entities, described by probability waves, their identities and positions fundamentally uncertain, all interacting through the quantum fields that permeate space. But let's try to build some intuition about this strange state of matter using an analogy that might help as you drift towards sleep. Think of a room full of people at a crowded party. When the room is extremely crowded and everyone is moving energetically, dancing and mingling freely, you can't really say that any particular person belongs to any particular group. Everyone is interacting with everyone else, constantly changing partners, moving freely through the space. This is like the quark-gluon plasma, where quarks and gluons move freely, constantly interacting but not bound into permanent structures. Now imagine the room slowly getting less crowded as people leave, and the energy level dropping as everyone gets tired. At some point, people start pairing off or forming small stable groups. Friends find each other and stick together. Couples form. Small conversation circles establish themselves. You've transitioned from a state of free mixing to a state of defined groups. This is analogous to what happened as the universe cooled and quarks became confined into protons and neutrons. The transition from quark-gluon plasma to confined matter happened at around 1 microsecond after the Big Bang, when the temperature had dropped to about 10 trillion degrees. This might still sound impossibly hot, and it is, but it represents a critical threshold. Below this temperature, the strong force, which had been acting more or less uniformly throughout the plasma, began to confine quarks into bound states. This process of confinement is one of the most fascinating phenomena in all of physics. Why do quarks become permanently bound at lower temperatures? The answer lies in the strange properties of the strong force itself, properties unlike any other force in nature. Most forces we're familiar with get weaker as you separate the objects experiencing them. Gravity gets weaker as you move away from a massive object. Electromagnetic force gets weaker as you separate charged particles. This makes intuitive sense, but the strong force behaves differently. It actually gets stronger as you try to pull quarks apart. Imagine trying to separate 2 quarks that are bound together in a proton. As you pull them apart, the gluons that mediate the strong force form what's called a flux tube between them, like an elastic band connecting them. The farther apart you pull the quarks, the more energy gets stored in this flux tube, and the stronger the force pulling them back together. It's as if they're connected by a spring that gets stiffer the more you stretch it. If you put enough energy into stretching this connection, something remarkable happens. The energy in the flux tube becomes so great that it spontaneously creates a new quark-antiquark pair from the vacuum. The original quark binds with one of these new quarks, and the other original quark binds with the other new quark. Instead of freeing the quarks, you've created two bound states where there was one before. This is why we never see isolated quarks in nature. The force that binds them has this strange property that it doesn't weaken with distance, at least not over the scales we can probe. Quarks are permanently confined, always bound together in groups of 2 or 3. But at extremely high temperatures, like those in the quark epoch, the thermal energy is so great that quarks and gluons can move freely despite the strong force. The energy density is so high that you have a sort of thermal ionization, analogous to how electrons can be stripped from atoms at high temperatures. The quarks are still interacting strongly with each other through gluon exchange, but they're not confined into individual protons and neutrons. They form a collective state, a plasma that fills all of space. As the universe expanded and cooled, passing through that critical temperature of around 10 trillion degrees, the quark-gluon plasma underwent what physicists call a phase transition. This is similar to water freezing into ice or steam condensing into liquid, a fundamental change in the state of matter driven by a change in temperature. The phase transition wasn't instantaneous or uniform. There would have been fluctuations, regions where quarks were confining into protons and neutrons, while adjacent regions remained as plasma, all mixing and transitioning on timescales unimaginably brief. But the overall result was clear. Within microseconds, the freely flowing quark-gluon plasma had transformed into a gas of protons, neutrons, and other particles made of confined quarks. This transformation is called hadronization, because protons and neutrons belong to a class of particles called hadrons, particles made of quarks. From this point forward, the universe would contain protons and neutrons as distinct entities, the fundamental building blocks that would eventually form atomic nuclei. Let's pause to appreciate the strangeness and wonder of this moment. For the first microsecond of its existence, the universe contained no protons, no neutrons, none of the particles that would become the constituents of ordinary matter. Instead, it was filled with this exotic plasma state, a soup of fundamental particles that we can barely recreate today in our most advanced experiments. And yet, from this undifferentiated soup emerged structure. As the temperature dropped through the critical threshold, quarks that had been moving freely suddenly found themselves confined, bound into triplets that would persist for billions of years. Some of the protons created in this phase transition are still around today, forming the nuclei of hydrogen atoms in your body, in the oceans, in interstellar clouds. They've survived unchanged for more than 13 billion years, but they were born in that first microsecond, crystallizing out of the primordial plasma as the universe cooled. Now, you might wonder, can we be sure this quark-gluon plasma really existed? After all, we're talking about a state of matter that vanished from the universe almost as soon as the universe began. How can we know? The answer is that we can recreate it, at least in tiny quantities and for incredibly brief moments. At particle colliders like the Relativistic Heavy Ion Collider in the United States and the Large Hadron Collider in Europe, physicists smash heavy atomic nuclei together at nearly the speed of light. In the collision zone, for a fleeting instant lasting perhaps 10 to the power of minus 23 seconds, the energy density becomes so great that the quarks and gluons in the colliding nuclei become deconfined. We create a tiny droplet of quark-gluon plasma, a few femtometers across. A bubble of the early universe materialized for less than the time it takes light to cross a proton. Physicists have studied these droplets extensively over the past 2 decades, and what they've found is fascinating. The quark-gluon plasma behaves like a nearly perfect fluid, meaning it flows with almost no viscosity. It's more fluid than water, more fluid than liquid helium. When you disturb it, it flows and ripples with remarkably little resistance. This wasn't what theorists initially expected. Many thought the plasma would behave more like a weakly interacting gas, but instead the quarks and gluons are strongly coupled, interacting intensely with each other, creating a fluid whose properties challenge our theoretical understanding. These experiments have given us a window into the first microsecond of cosmic history. We can measure the properties of this primordial state of matter, test our theories, refine our understanding. It's one of the few areas where particle physics experiments can directly illuminate cosmology, where laboratory work connects to the story of the universe's beginning. As you lie here in the quiet darkness, consider the journey that matter has taken. In the beginning, after inflation ended, there was just this undifferentiated plasma, quarks and gluons and other particles all mixed together in a hot, dense soup. This state persisted for about a microsecond, an eternity on the timescale of the first moments, but still impossibly brief by any human measure. Then, as the universe cooled through the critical temperature, confinement set in. Quarks bound together into protons and neutrons. The universe went from being a continuous plasma to containing discrete particles, from uniformity to structure, from simplicity to the first level of complexity. This wasn't the end of the story, of course. The protons and neutrons would go on to fuse into the first atomic nuclei in the first few minutes. Hundreds of thousands of years later, those nuclei would capture electrons to form the first atoms. Hundreds of millions of years after that, those atoms would gather into clouds that collapsed into stars. In those stars, more complex nuclei would be forged, and eventually, those atoms would arrange themselves into planets, oceans, living cells, and conscious beings capable of understanding their own history. But it all began with this transition, this crystallization of structure from the primordial soup. The quarks that make up your body, the up quarks and down quarks in every proton and neutron of every atom, emerged from that plasma in the first microsecond. They've been confined ever since, never alone, always bound in triplets, patiently waiting through billions of years of cosmic evolution to eventually be part of you, here, now, contemplating the moment of their origin. The quark-gluon plasma was the universe's crucible, the forge in which ordinary matter was shaped. It was a state of perfect democracy, where no quark was bound and all moved freely, a fleeting moment of fundamental symmetry before the universe began organizing itself into structures and hierarchies. And though this state vanished from the cosmos almost immediately, leaving behind a universe of confined quarks and established particles, we carry its legacy in every atom of our being. We are made of the products of that phase transition, constructed from particles that crystallized out of the primordial soup. There's something poetic about the fact that we can recreate this state in our colliders, that we can bring back, for the briefest instant, a piece of the universe as it was in its first microsecond. We can study our origins not just by looking backward through telescopes at distant galaxies, but by looking inward at the fundamental constituents of matter, by smashing particles together and watching what emerges from the collision, seeing echoes of creation in the debris. As sleep begins to wash over you, let yourself feel the connection to that ancient moment. The particles in your body remember, in their quantum way, the transition from freedom to confinement, from plasma to proton, from undifferentiated soup to structured matter. They carry in their nature the imprint of that phase transition, the signature of the universe's cooling, the mark of confinement. You are made of confined quarks, bound together by gluons exchanging between them at rates too fast to comprehend, held in eternal embrace by a force that grows stronger with separation. These quarks have been bound since that first microsecond, stable and unchanging through the vast sweep of cosmic history. Before there were stars, before there were galaxies, before there were atoms, there was the quark-gluon plasma. And from that plasma, in the cooling aftermath of inflation, matter as we know it emerged. The universe found its form, its structure, its building blocks. And 13.8 billion years later, some of those building blocks arranged themselves into you, capable of understanding the story of their own creation. The first elements. How were the atoms forged in the first few minutes? Imagine you could hold in your hand a lump of the oldest matter in the universe, material that has remained largely unchanged since the cosmos was just minutes old. In a sense, you already can. About 25% of your body's mass is helium, and nearly all of that helium was created not in stars, but in the first few minutes after the Big Bang. Every breath you take contains helium atoms that have existed since the universe was younger than a sitcom episode, forged in the cosmic furnace when space itself was hotter than the core of any star that would ever shine. As you settle into rest tonight, Let's explore those first minutes, the brief window when the universe became a cosmic fusion reactor, creating the first atomic nuclei and establishing the chemical composition that would persist for billions of years. This is the story of Big Bang nucleosynthesis, one of the most successful predictions in all of science. A moment when theory and observation align so perfectly that we can peer back across 13.8 billion years and know, with remarkable precision, what was happening when the universe was younger than your morning coffee takes to cool. After the quark-gluon plasma transitioned into protons and neutrons at about 1 microsecond, the universe continued expanding and cooling. But it was still far too hot for these protons and neutrons to stick together. Anytime they collided with enough energy to briefly bind, the intense thermal radiation would blast them apart again. The universe was like a room so hot that ice cubes would melt instantly upon forming. Protons and neutrons existed as a hot gas, colliding constantly but unable to form stable combinations. As you lie here in the darkness, consider what was happening during this period. The universe was expanding rapidly, doubling in size every few seconds. As it expanded, it cooled, following that fundamental relationship we discussed before. Expansion equals cooling. The temperature, which had been trillions of degrees when the protons and neutrons first formed, was dropping steadily, passing through billions of degrees, heading toward the critical threshold where nuclear fusion could begin to create stable nuclei. This threshold was reached at about 3 minutes after the Big Bang, when the temperature had cooled to around 1 billion degrees. That's still about 70 times hotter than the core of the Sun, but it's cool enough for the universe to become a cosmic fusion factory. To understand what happened next, we need to talk about what holds atomic nuclei together. You might remember that protons are positively charged, and like charges repel each other. So if you try to bring two protons close together, they push apart through electromagnetic repulsion. This is why atomic nuclei don't just form spontaneously in ordinary conditions. You need enormous energy to overcome this electromagnetic barrier and push protons close enough together that the strong nuclear force, which only operates over very short ranges, can take over and bind them together. In the cores of stars, this energy comes from the intense pressure and temperature created by gravity. In the early universe, it came from the overall thermal energy filling space. At temperatures above 1 billion degrees, particles are moving so fast that when protons and neutrons collide, they sometimes overcome the electromagnetic repulsion and get close enough for the strong force to bind them together. The simplest nucleus to form is deuterium, sometimes called heavy hydrogen. Deuterium consists of 1 proton and 1 neutron bound together. When a proton and neutron collide with enough energy in the right way, they can stick together, forming a deuterium nucleus. This process began happening around 3 minutes after the Big Bang, as soon as the temperature dropped enough that deuterium nuclei wouldn't be immediately blasted apart by thermal radiation. The formation of deuterium was like opening a floodgate. Once you have deuterium, you can build heavier elements through additional fusion reactions. A deuterium nucleus can collide with another proton or neutron and fuse into helium-3, which has 2 protons and 1 neutron, or into tritium, which has 1 proton and 2 neutrons. These can then fuse with additional particles, or with each other, to create helium-4, the most stable light nucleus, consisting of 2 protons and 2 neutrons. Picture the universe during these few minutes as a cosmic soup, where nuclear reactions are happening everywhere at once. Protons and neutrons are still the main ingredients, but now they're occasionally sticking together when they collide, building up chains of fusion reactions. A proton captures a neutron, forming deuterium. That deuterium quickly captures another proton or neutron. The resulting nucleus might capture yet another particle, or it might collide with another light nucleus and fuse into something heavier. The most common end product of this process was helium-4. This makes sense when you understand nuclear physics. Helium-4 is exceptionally stable. It has 2 protons and 2 neutrons arranged in what's essentially a perfectly balanced configuration. It's much more tightly bound than deuterium, or helium-3, or tritium. Once you form a helium-4 nucleus, it tends to stay that way. It's the nuclear equivalent of a marble settling into a deep bowl. It's found a low energy state and doesn't easily get kicked out of it. By about 20 minutes after the Big Bang, the universe had cooled enough that fusion reactions essentially stopped. The cosmic factory shut down. The temperature had dropped below about 100 million degrees, no longer hot enough to overcome the electromagnetic barriers needed for fusion. From this point forward, the mix of light elements was essentially fixed. About 75% of the ordinary matter in the universe was hydrogen, single protons that never fused with anything. About 25% was helium-4, and there were trace amounts, measured in parts per 100,000 or parts per million, of deuterium, helium-3, and lithium-7. Now, here's where the story becomes truly remarkable. In the 1940s and 50s, physicists including Ralph Alpher, Robert Herman, and George Gamow worked out the detailed nuclear physics of what should happen during these first minutes. They calculated, using the known properties of nuclear reactions and the predicted conditions in the early universe, exactly how much of each light element should be produced. These calculations depend on several factors: the temperature and density of the universe at various times, the ratio of protons to neutrons at the start of nucleosynthesis, the rate at which the universe was expanding, which determines how long the window for fusion remained open, the cross-sections or probabilities of various nuclear reactions, which tell us how likely protons and neutrons are to fuse when they collide. All of these factors can be calculated from basic physics, and when you work through the math carefully, you get very specific predictions. The theory predicts that about 25% of ordinary matter should end up as helium-4. It predicts specific abundances for deuterium, about 25 parts per million, for helium-3, about 10 parts per million, for lithium-7, about 10 parts per billion. These are precise, quantitative predictions. They're not vague statements that some helium should exist. They're exact numbers, ratios that the theory says must hold if the Big Bang model is correct. And here's the beautiful part. When astronomers look at the oldest, most pristine objects in the universe, objects whose composition hasn't been significantly altered by stellar processing, they measure abundances that match these predictions almost exactly. Let that sink in as you drift towards sleep. We can calculate what should have happened in the first 20 minutes of cosmic history, and when we look out at the universe today, more than 13 billion years later, we see exactly the mix of elements that the theory predicts. The helium abundance in old metal-poor stars and in primordial gas clouds is about 25%, just as predicted. The deuterium abundance in distant gas clouds, measured by the absorption lines they produce in the light from even more distant quasars, matches the predictions. The lithium abundance, though it has some puzzles we're still working to understand, is roughly what the theory expects. This is one of the most powerful confirmations of the Big Bang model. It's not just that the theory can explain what we see, it's that the theory predicted what we should see before we had good observations. And then when the observations improved, they matched the predictions. This is how science builds confidence. Through successful predictions that could have been wrong, but turned out to be right. Think about the chain of reasoning here. We observe that the universe is expanding. We use general relativity to calculate what the universe must have been like at earlier times. We determine the temperatures and densities at various moments. We apply nuclear physics to figure out what reactions should occur. We calculate the abundances of light elements that should result. And then we go out and measure those abundances in the actual universe, and they match. Each step in this chain could have failed. The universe might have been expanding, but not from a hot, dense state. The physics might have been different in the early universe. The predicted abundances might not have matched what we observe. But at each step, nature has cooperated. The evidence has aligned with the theory. The universe has confirmed our mathematical reconstruction of its own history. There's something almost miraculous about this when you really contemplate it. The universe was kind enough to write its history into the abundances of its lightest elements. Every helium atom in your body is like a timestamp, a marker saying, "I was created when the universe was between 3 and 20 minutes old." Every rare deuterium nucleus is a message from that brief fusion era. The very chemistry of the cosmos preserves the memory of those first minutes. Let's think about what didn't form during Big Bang nucleosynthesis. Why did the process stop at helium and trace amounts of lithium? Why didn't the early universe create carbon, oxygen, iron, and all the other elements we see around us? The answer has to do with timing and nuclear physics. To build elements heavier than lithium, you need to bridge what's called the mass 5 and mass 8 gaps. There are no stable nuclei with mass number 5 or mass number 8. Lithium-7, with 3 protons and 4 neutrons, can capture another proton or neutron to form a nucleus with mass 8, but that nucleus is unstable and immediately falls apart. It's like trying to build a bridge with a missing section in the middle. You can't get across. In stars, these gaps are eventually bridged through more complex processes involving triple collisions and reactions that require millions of years of sustained fusion. But in the early universe, the window of opportunity was only about 17 minutes, from 3 minutes to 20 minutes. The universe was expanding and cooling too rapidly for these more complex processes to occur. By the time helium-4 had formed, the temperature had already dropped too low for further fusion. So Big Bang nucleosynthesis produced hydrogen and helium, with traces of a few other light elements, and then it stopped. All the heavier elements, everything in the periodic table from carbon to uranium, would have to wait. They would be created later, billions of years later, in the cause and death throes of stars. But that's a story for another night. The 25% helium abundance is particularly important. This number is remarkably robust. It doesn't depend much on the exact conditions of the early universe. Whether you assume slightly different expansion rates or slightly different particle physics, you always get about 25% helium. The reason has to do with the neutron to proton ratio at the start of nucleosynthesis. In the very early universe, neutrons and protons could convert into each other through weak interactions involving neutrinos. A neutron could decay into a proton, an electron, and an antineutrino. A proton could capture an electron or neutrino and become a neutron. At high temperatures, these reactions happened rapidly enough to maintain equilibrium, with the neutron to proton ratio determined by the slight mass difference between neutrons and protons and the temperature. As the universe cooled and expanded, these reactions became slower. Eventually, at about 1 second after the Big Bang, they became too slow to maintain equilibrium. The neutron to proton ratio froze in at about 1 neutron for every 6 protons. From this point on, the only process changing the ratio was neutron decay. Free neutrons are unstable and decay into protons with a half-life of about 10 minutes. By the time nucleosynthesis began at 3 minutes, some of the neutrons had decayed, leaving a ratio of about 1 neutron for every 7 protons. Nearly all these neutrons ended up in helium-4 nuclei, which have equal numbers of neutrons and protons. When you work through the arithmetic, you find that this naturally produces about 25% helium by mass. This is elegant. The helium abundance is determined by fundamental physics, by the mass difference between neutrons and protons, by the strength of the weak interaction, by the expansion rate of the universe. All these factors conspire to produce the quarter helium, 3/4 hydrogen mix that we observe. As you rest here, breathing steadily, consider that every breath contains atoms with this history. The hydrogen you breathe, the hydrogen in the water in your cells, most of it has been around since 3 minutes after the Big Bang. Single protons that never fused with anything during nucleosynthesis. The helium in your breath, rare as it is in Earth's atmosphere, was created in that first 20 minutes. Some of the heavier elements in your body, the carbon, the oxygen, the nitrogen, the calcium in your bones, the iron in your blood, those came later, forged in stars that lived and died billions of years after nucleosynthesis. But the lightest elements, the foundation of cosmic chemistry, they date back to the beginning. There's a beautiful simplicity to nucleosynthesis when you step back and see the whole picture. The universe started hot and dense. As it cooled, it went through a phase transition where quarks confined into protons and neutrons. As it continued cooling, it went through another transition where protons and neutrons fused into light nuclei. Each transition happened at a characteristic temperature, a threshold where the physics changed, where new structures could form that couldn't exist at higher temperatures. These transitions were inevitable, written into the laws of physics and the initial conditions of the universe. Given a hot, expanding universe with the fundamental forces and particles we observe, nucleosynthesis had to happen. The abundances had to come out roughly as we calculate. The universe had to emerge from its first 20 minutes with the chemical signature we observe today, and we can verify this. We can look at distant galaxies, seeing them as they were billions of years ago, and measure their helium content. We can analyze the oldest stars in our galaxy, stars that formed from nearly pristine material shortly after the Big Bang. We can study the absorption lines in the spectra of distant quasars, revealing the composition of intervening gas clouds. Everywhere we look, in every epoch we can observe, we see the chemical signature of those first minutes. This is why Big Bang nucleosynthesis is considered one of the 3 pillars supporting the Big Bang theory. along with the expansion of the universe and the cosmic microwave background. Each of these provides independent evidence, and they all tell the same story. The universe was once much hotter and denser. It has been expanding and cooling for billions of years, and the early moments of this expansion left permanent marks that we can still detect today. As sleep draws near, let yourself feel the connection to that ancient fusion era. The atoms in your body carry memories of different epochs. The lightest elements remember those first minutes. The heavier elements remember the lives and deaths of stars. You are made of cosmic history, layer upon layer. Each element a chapter in the story of how simple hydrogen, forged in the Big Bang, was transformed through billions of years into the complex chemistry that makes life possible. The universe spent just 17 minutes as a fusion reactor, creating the light elements that would remain essentially unchanged for eons. That brief period established the chemical baseline of the cosmos, the starting composition from which all future complexity would emerge. Stars would later enrich the universe with heavier elements, but they would always be adding to that initial mixture, that 3-to-1 ratio of hydrogen to helium that came out of the first 20 minutes. The Cosmic Dark Ages. Why was the universe suddenly invisible? Imagine a fog so thick that light cannot travel through it, so dense that if you held your hand in front of your face, you would see nothing. Now imagine this fog filling not just a valley or a city, but the entire universe, every cubic inch of space, stretching in all directions without end. This was the state of the cosmos for hundreds of thousands of years after the Big Bang, a period when the universe was literally opaque, when light could not travel freely, when darkness reigned supreme despite temperatures hot enough to vaporize any material we know today. As you settle into rest tonight, let's explore this mysterious period, the Cosmic Dark Ages, when the universe transformed from an opaque fog into the transparent cosmos we observe today. It's a story of cooling and clearing, of electrons finding their home in atoms, of light finally breaking free to travel across the universe. And it's a story that left behind the most ancient light we can see, a message from the edge of visibility, a snapshot of the universe at the moment it became transparent. After the drama of the first 20 minutes, after nucleosynthesis had created the light elements, the universe settled into a long period of relatively uneventful expansion and cooling. The cosmic factory had shut down. No more fusion was occurring. The universe was now filled with a plasma of nuclei, mostly hydrogen and helium, along with free electrons and photons, all expanding and cooling together as space itself grew larger. But something important was still missing. There were no atoms yet, not in the sense we usually mean. The nuclei existed, protons and helium nuclei floating freely through space. The electrons existed, zipping around at high speeds, but they weren't bound together into neutral atoms. The universe was still too hot for that. To understand why, think about what an atom actually is. An atom consists of a nucleus, containing protons and neutrons, with electrons bound to it through electromagnetic attraction. The positive charge of the nucleus attracts the negative charge of the electrons, and quantum mechanics determines the specific orbits or clouds where electrons can exist around the nucleus. This is the structure of matter we're familiar with, the foundation of chemistry and all the complexity that chemistry enables. But this structure requires relatively gentle conditions to form and persist. If you take an atom and heat it up enough, or bombard it with enough energetic radiation, you can knock the electrons off the nucleus. This process is called ionization. The atom breaks apart into a positively charged nucleus and one or more free negatively charged electrons. You've turned neutral matter into a plasma, a gas of charged particles. In the early universe, the conditions were far too violent for neutral atoms to exist. The thermal radiation filling space was so intense, the photons so energetic, that any electron that tried to bind to a nucleus would immediately be knocked free again. It was like trying to build a house in a hurricane. The pieces might come together briefly, but they'd be torn apart before they could establish any lasting structure. This plasma state had a crucial property. It was opaque to light. Let's explore why, because this is key to understanding the cosmic dark ages. When light travels through neutral matter, through ordinary atoms, it can usually pass through relatively unimpeded unless the photons have exactly the right energy to be absorbed by electrons jumping between energy levels in atoms. But when light travels through a plasma, through a gas of free charged particles, it interacts much more strongly. The photons scatter off the free electrons constantly, bouncing from one to another like a ball in a pinball machine. This scattering meant that photons couldn't travel far in straight lines. A photon would move a short distance, scatter off an electron and change direction, move another short distance, scatter again, and so on. The path of any individual photon through this plasma was like a random walk, a zigzagging journey where it never got very far from where it started, despite moving at the speed of light. Picture the universe during this period, from about 20 minutes after the Big Bang to about 380,000 years later. It's filled with this glowing plasma, hot and dense, expanding and cooling, but opaque. If you could somehow have existed then and opened your eyes, you wouldn't see anything. Light couldn't travel to you from any distance. You'd be surrounded by a glowing fog that scattered every photon before it could reach you. The universe was dark, not because there was no light, but because the light couldn't travel freely. This might seem paradoxical. How can something be both glowing and dark? The answer is that the plasma was emitting light at every point, but that light couldn't propagate. It was trapped, scattered endlessly, unable to escape from the region where it was created. The universe was like the inside of a cloud or a dense fog, luminous in principle but effectively dark because no information could be transmitted through light. As you lie here in the quiet darkness of your room, recognize that this darkness is very different from the cosmic dark ages. Your room is dark because there's little light being emitted, and what light exists is absorbed by the walls and objects around you. The early universe was dark because light was being scattered, trapped in an endless dance with free electrons, unable to travel far enough to carry information or illuminate anything distant. But the universe was cooling as it expanded, following that fundamental relationship we've returned to again and again. The temperature, which had been billions of degrees after nucleosynthesis, was dropping steadily. After thousands of years, it had cooled to millions of degrees. After hundreds of thousands of years, it was approaching a critical threshold, the temperature at which electrons could finally bind to nuclei and stay bound, where neutral atoms could form and persist. This threshold is around 3,000 degrees, about half the temperature of the sun's surface. At this temperature, the typical photon in the universe no longer has enough energy to immediately ionize a newly formed hydrogen atom. Electrons can bind to protons, forming neutral hydrogen, and those atoms will remain neutral for significant periods of time. The transition happened at approximately 380,000 years after the Big Bang, when the temperature had cooled to about 3,000 degrees. This moment is called recombination, though that's actually a misleading name because the electrons and nuclei were combining for the first time, not recombining. The name stuck from early cosmological models that didn't fully understand the sequence of events, but we're stuck with it now. Recombination didn't happen instantly everywhere. It was a gradual process that took perhaps tens of thousands of years to complete throughout the universe. Electrons began binding to nuclei in increasing numbers. The fraction of matter that was ionized dropped from nearly 100% to nearly 0%. The plasma transitioned into a gas of neutral atoms, and when this happened, something remarkable occurred. The universe became transparent. Neutral atoms don't scatter light nearly as effectively as free electrons do. Photons can pass through a gas of neutral atoms without much interaction, unless they happen to have exactly the right energy to be absorbed by an electron transition. Most photons don't, so they travel freely. The cosmic fog cleared. Light that had been trapped, scattered endlessly, suddenly found itself able to travel in straight lines across vast distances. This is one of the most important moments in cosmic history. It's called the epoch of last scattering, or sometimes photon decoupling. Before this moment, light and matter were tightly coupled, constantly interacting, unable to go their separate ways. After this moment, they decoupled. Photons could travel freely through space, while matter went on to form structures under the influence of gravity. The photons that were released at this moment, that scattered off electrons one last time, and then found themselves free to travel through the newly transparent universe, are still traveling today. They've been stretched by the expansion of space. Their wavelengths extended from visible and infrared light into microwaves, but they're still here, filling the universe, and we can detect them. This is the cosmic microwave background, the CMB, the most ancient light we can observe. When you see images of the CMB, like those from the Planck satellite or WMAP, you're seeing a snapshot of the universe at 380,000 years old. at the moment of recombination, when the fog cleared and light broke free. Let that settle into your mind as you drift towards sleep. The universe has a surface of last scattering, a cosmic horizon beyond which we cannot see with light. Not because nothing is there, but because before that moment, light couldn't travel freely. The CMB is the light from that surface, the glow of the universe at the moment it became transparent, stretched and cooled by billions of years of cosmic expansion, but still carrying information about conditions at that ancient time. The CMB is remarkably uniform. Its temperature is the same in all directions to about 1 part in 100,000. This uniformity tells us that the universe at recombination was remarkably smooth, with only tiny variations in density from place to place. But those tiny variations are crucial. They're the seeds from which all future structure would grow. Slightly denser regions would gravitationally attract surrounding matter, growing denser still, eventually collapsing into the first stars and galaxies. The tiny ripples we see in the CMB are the ancestors of the great cosmic web of galaxies we observe today. After recombination, after the universe became transparent, it entered what cosmologists call the Dark Ages. This might seem confusing. Didn't the universe just become transparent? Didn't light become free to travel? So why is this period called the Dark Ages? The Dark Ages are dark not because the universe is opaque, but because there are no sources of visible light. After recombination, the universe consists of neutral hydrogen and helium gas, along with the stretched cosmic microwave background radiation. But there are no stars yet. No galaxies, no quasars, nothing producing visible light. If you could somehow observe the universe during this period, you'd see nothing in visible wavelengths. The darkness would be complete, not the scattering darkness of the plasma era, but the empty darkness of a universe waiting for its first lights to turn on. This period, from about 380,000 years to about 150 million years after the Big Bang, is one of the most mysterious epochs in cosmic history. We have no direct observations of it. The CMB shows us the universe at the start of this period, and observations of the earliest galaxies and quasars show us the universe near the end of it. But the Dark Ages themselves remain largely hidden from view. During this time, the universe was expanding and cooling, but more importantly, it was evolving under the influence of gravity. Dark matter, that mysterious substance that doesn't interact with light but does have gravity, was clumping together in certain regions. These clumps of dark matter created gravitational wells that attracted the ordinary matter, the hydrogen and helium gas. The gas began flowing toward the densest regions, beginning the process of structure formation that would eventually produce galaxies. But this process took time. Gravity is patient. The tiny density fluctuations present at recombination, variations of only 1 part in 100,000, had to grow through gravitational instability. Denser regions would attract matter from their surroundings, becoming denser still, which would allow them to attract even more matter in a self-reinforcing cycle. But this growth was slow, at least on human timescales, taking millions of years for the first significant structures to emerge. As you rest here, imagine the universe during these dark ages. It's filled with neutral gas, mostly hydrogen, with some helium mixed in. This gas is dark to our eyes, emitting no visible light. The only radiation is the cosmic microwave background, now stretched into infrared wavelengths and continuing to cool. The gas is distributed almost uniformly, but not quite. There are regions slightly denser than average, and these are slowly drawing in more gas from their surroundings. The universe is cold now, relatively speaking. By 1 million years after the Big Bang, the temperature has dropped to a few thousand degrees. By 10 million years, it's hundreds of degrees. By 100 million years, it's below freezing by human standards. The gas is cooling, the radiation is fading, and the universe is becoming a truly dark and cold place. But hidden in this darkness, great events are preparing. In the densest regions, where dark matter has accumulated and gas is flowing inward most rapidly, the first stars are beginning to form. Clouds of hydrogen are collapsing under their own gravity, heating up as they compress, eventually becoming hot and dense enough at their cores for nuclear fusion to begin. The moment when the first star ignited, when nuclear fusion first began in a collapsed gas cloud, marks the end of the Dark Ages. Suddenly, there was light again. Not the uniform glow of the plasma era, or the fading echo of the CMB, but point sources, stars shining in the darkness. This epoch is called Cosmic Dawn. the moment when the universe lit up after hundreds of millions of years of darkness. The first stars were probably very different from the stars we see today. They formed from pristine gas, hydrogen and helium with no heavier elements, and this affected their properties. They were likely extremely massive, perhaps hundreds of times the mass of our Sun, and they burned hot and bright, living fast and dying young in spectacular supernova explosions that scattered the first heavy elements into space. These first stars began a process that would transform the universe. Their ultraviolet radiation began reionizing the hydrogen gas around them, turning it from neutral atoms back into plasma. But now, in discrete regions around these first light sources, rather than uniformly throughout space. As more stars formed, these ionized bubbles grew and merged, and eventually, by about 1 billion years after the Big Bang, the universe was fully reionized. The period of neutral atoms that began at recombination had ended, and the universe returned to an ionized state, though now much more dilute and structured than the primordial plasma. But here's the key difference. The reionized universe was still transparent. Even though hydrogen was ionized again, it was now so dilute that photons could travel freely. The free electrons were too sparse to effectively scatter light, so the universe remained transparent, as it has been ever since, and as it will remain into the indefinite future. As sleep approaches, consider the journey the universe took through these epochs. It began as an opaque plasma, glowing but dark because light couldn't travel. It cooled and became transparent at recombination, allowing light to travel freely for the first time. It entered a true dark age, transparent but empty, with no sources of light. And then it was gradually illuminated from within as stars formed, creating islands of light that grew and merged until the whole cosmos was lit up. This sequence of transformations is written into observations we can make today. The cosmic microwave background tells us about recombination. The spectra of distant quasars, which show absorption from neutral hydrogen, tell us about reionization. The oldest galaxies we can observe show us the end of the dark ages and the beginning of cosmic dawn. Each observation is a piece of the puzzle, and together they reveal the story of how the universe evolved from opaque fog to transparent darkness to illuminated cosmos. The clearing of the cosmic fog at recombination is also what makes cosmology possible as an observational science. Because the universe became transparent then, we can see back to that moment. The CMB is like a baby picture of the universe, showing its appearance at 380,000 years old. Everything we observe in the universe, every galaxy and star and planet, formed after this moment, after the fog cleared, in the transparent universe that emerged from recombination. Before recombination, we cannot see with light. The universe is opaque to us, hidden behind the glowing wall of the cosmic microwave background. This is a fundamental horizon of observation. We can infer what happened before by using theory and by detecting other messengers like gravitational waves or neutrinos. But the light from before recombination cannot reach us. It's trapped, scattered, absorbed into the plasma that existed then. The first light. What can the cosmic microwave background tell? Let's imagine you could take a photograph of a baby and then, by examining every detail of that picture, predict what kind of person they would become, where they would live, what communities they would form. It sounds impossible, yet this is essentially what cosmologists can do with the cosmic microwave background. This ancient light, released when the universe was just 380,000 years old, contains within its subtle patterns the blueprint for everything that would follow. Every galaxy, every star cluster, every structure in the cosmic web. And remarkably, this baby picture of the universe was discovered entirely by accident. As you settle into rest tonight, let's explore the cosmic microwave background, the oldest light we can see, the most direct window into the early universe, and one of the most important discoveries in the history of science. It's a story that begins with confusion, continues through technological marvels, and ends with profound understanding of our cosmic origins. The year was 1964. Two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Telephone Laboratories in New Jersey, preparing a large horn antenna for radio astronomy observations. They were meticulous researchers who wanted to eliminate every possible source of interference and noise from their measurements. They needed their instrument to be as quiet as possible so they could detect faint radio signals from space. But no matter what they did, they couldn't get rid of a persistent hiss in their data. The noise was there day and night, summer and winter, coming equally from all directions in the sky. It was as if the entire universe was producing a steady, uniform radio signal that they couldn't eliminate. They checked every component of their antenna. They even cleaned out pigeons that had been roosting in the horn, removing what they delicately called a white dielectric material, thinking perhaps bird droppings were somehow responsible for the signal. Nothing worked. The hiss remained. What Penzias and Wilson had discovered, though they didn't realize it at first, was the cosmic microwave background. They were detecting the stretched, cooled remnant of the light released at recombination. The moment when the universe became transparent, they were seeing, or rather hearing through their radio antenna, the afterglow of the Big Bang itself. The realization of what they'd found came through a fortunate connection. A colleague mentioned that a group of physicists at nearby Princeton University, led by Robert Dicke, were actually building an antenna to search for exactly this kind of signal. Dicke's team, based on theoretical work, predicted that if the Big Bang theory was correct, there should be a uniform background of radiation filling the universe, cooled by cosmic expansion to just a few degrees above absolute zero, appearing as microwave radiation. When Dicke learned about Penzias and Wilson's mysterious noise, he immediately understood what it was. The story goes that when his colleagues told him about the Bell Labs discovery, Dicke simply said, "Well, boys, we've been scooped." The cosmic microwave background had been found not by those who were looking for it, but by those who were trying to eliminate it as noise. Penzias and Wilson published their findings in 1965, and the discovery would eventually earn them the Nobel Prize in Physics. The cosmic microwave background provided powerful evidence for the Big Bang theory, which at that time was still competing with alternative models like the steady-state theory. Here was direct observational confirmation that the universe had been in a hot, dense state in the past and had cooled as it expanded. But as you drift towards sleep, let's think about what this radiation actually is and why it's so important. The CMB is, quite literally, light from the edge of visibility. It's the oldest light that can reach us, emitted when the universe was 380,000 years old. Every photon in the CMB has been traveling through space for more than 13 billion years, and they're still arriving now constantly from all directions. When these photons were released at recombination, they were primarily visible and infrared light, with wavelengths of around 1 micrometer, corresponding to a temperature of about 3,000 degrees. But space itself has been expanding since then, and as space expands, it stretches the wavelengths of light traveling through it. The light has been stretched by a factor of about 1,100. So what started as visible light is now microwave radiation with wavelengths around 1 millimeter, corresponding to a temperature of about 2.7 degrees above absolute zero. This stretching is called cosmological redshift, and it's one of the most important concepts in cosmology. The light itself hasn't lost energy in the normal sense. Rather, space has expanded, carrying the light with it and stretching its wavelength in the process. The CMB has been cooled by the expansion of the universe, and its current temperature tells us by how much space has expanded since recombination. The initial measurements by Penzias and Wilson and subsequent observations through the 1970s and early 80s confirmed that the CMB has a nearly perfect blackbody spectrum, meaning it has exactly the distribution of wavelengths you'd expect from a hot object in thermal equilibrium. This perfect blackbody spectrum is itself profound evidence for the Big Bang. It's exactly what you'd predict if the entire universe was once in thermal equilibrium, at a uniform temperature and then cooled by expansion. But the real breakthrough in understanding the CMB came from measuring not just its average temperature, but its tiny variations in temperature from place to place across the sky. These variations, called anisotropies, contain an enormous amount of information about the early universe. In 1989, NASA launched the Cosmic Background Explorer satellite, known as COBE. One of COBE's instruments was designed to map the temperature of the CMB across the entire sky with unprecedented precision. What it found was remarkable. The CMB is extraordinarily uniform, having almost exactly the same temperature in all directions, but not perfectly uniform. There are tiny fluctuations, variations of only about 1 part in 100,000, where some regions are slightly warmer and others slightly cooler. When the COBE team leader, George Smoot, presented these results in 1992, he called them the Holy Grail of cosmology and likened them to seeing the face of God. What he meant was that these temperature fluctuations are the imprints of the primordial density variations, the seeds from which all cosmic structure grew. They represent the quantum fluctuations from the inflationary epoch, stretched to cosmic scales and frozen into the matter distribution at recombination. Let's pause here to understand what these fluctuations mean. At the moment of recombination, the universe was remarkably smooth, but not perfectly smooth. Some regions were slightly denser than average, others slightly less dense. These density variations produced temperature variations in the CMB through several physical effects. In denser regions, gravity was slightly stronger, so photons had to work harder to escape, losing energy in the process and appearing slightly cooler. In other regions, variations in the motion of matter created temperature differences through the Doppler effect. The interplay between matter, radiation, and gravity before recombination created a pattern of fluctuations with specific statistical properties, a particular distribution of sizes and amplitudes. These fluctuations are not random. They encode information about the fundamental properties of the universe: its age, its composition, its geometry, its expansion rate. By carefully measuring the pattern of fluctuations across the sky, cosmologists can extract values for these parameters with remarkable precision. After COBE came even more sophisticated missions. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, mapped the CMB with much higher resolution and precision. Then came the European Space Agency's Planck satellite, launched in 2009, which provided the most detailed map of the CMB we have to date. These missions revealed the CMB in exquisite detail. The maps they produced show the temperature variations across the sky, with colors representing regions that are slightly warmer or cooler than average. To the untrained eye, they look like abstract art, mottled patterns of color. But to cosmologists, they're a treasure trove of information, a cosmic Rosetta Stone that allows us to decode the early universe. One of the most important ways to analyze the CMB is through what's called the power spectrum. This is a mathematical tool that tells us the typical size of the hot and cold spots in the CMB map. Some features in the CMB are large, spanning many degrees across the sky. Others are small, visible only at fine angular scales. The power spectrum quantifies how much temperature variation exists at each scale. The shape of the CMB power spectrum is determined by the physics of the early universe. The largest scale corresponds to the size of the cosmic horizon at recombination, how far light could have traveled, and how far regions could have been in causal contact. Smaller scales are set by the physics of sound waves propagating through the plasma before recombination. Yes, sound waves. This might seem strange, but before recombination, the universe was filled with a plasma that could support acoustic oscillations, compressions, and rarefactions propagating through the fluid. Regions that were slightly denser would gravitationally attract surrounding matter, compressing further, but this compression would heat the plasma, increasing pressure which would push back, causing the region to expand again. This created oscillations, cosmic sound waves resonating through the primordial plasma. At recombination, when the universe became transparent, these oscillations froze in place. The CMB captured a snapshot of the plasma at that moment, showing regions caught at different phases of oscillation. Some regions were at maximum compression, some at maximum rarefaction, some in between. This created a characteristic pattern of peaks and troughs in the power spectrum, a series of acoustic peaks that encode information about the cosmic sound waves. The precise location and height of these peaks depend on the properties of the universe. The angle subtended by the first peak tells us about the geometry of space, whether it's flat, curved like a sphere, or curved like a saddle. The ratio between different peaks tells us about the relative amounts of ordinary matter and dark matter. The overall amplitude tells us about the strength of the primordial fluctuations. Every detail matters, and every detail constrains our cosmological models. As you lie here in the darkness, consider the remarkable fact that we can use measurements of ancient light to determine the composition of the universe. From the CMB power spectrum, we've learned that ordinary matter, the atoms that make up stars, planets, and people, constitutes only about 5% of the universe's energy content. Dark matter, which we can't see but which reveals itself through gravity, makes up about 27%. And dark energy, the mysterious component driving the accelerating expansion of the universe, constitutes about 68%. These numbers come from fitting theoretical models to the observed CMB data. We have equations that describe how the universe evolves, how matter and radiation interact, how structures grow. These equations contain parameters whose values we don't know from first principles. But by comparing the predictions of our models with the observed CMB, we can determine what values these parameters must have to match what we see. The fact that we can do this at all is remarkable. The fact that when we do it, we get consistent answers that agree with many other independent observations is even more remarkable. The CMB tells us the universe is 13.8 billion years old, and this agrees with the ages of the oldest stars. It tells us the geometry of space is flat or very nearly so, and this agrees with other cosmological observations. It tells us the ratio of dark matter to ordinary matter, and this agrees with what we infer from galaxy formation and large-scale structure. The tiny temperature fluctuations in the CMB are also directly connected to the structures we see in the universe today. The slightly denser regions imprinted in the CMB are the seeds that grew, through gravitational instability over billions of years, into the galaxies and galaxy clusters we observe. We can trace the lineage from CMB fluctuations to cosmic structures. The largest clusters of galaxies today formed from the largest overdensities in the CMB. The voids between galaxy clusters today correspond to underdense regions in the CMB. There's a beautiful continuity here. The quantum fluctuations during inflation were stretched to macroscopic scales. They created density variations in the matter distribution. These variations produced temperature variations in the CMB at recombination. Those same density variations then grew through gravity to produce galaxies and clusters. Every galaxy in the universe, including our own Milky Way, can trace its origin to a tiny fluctuation in the primordial quantum field, a fluctuation now visible as a subtle temperature variation in the cosmic microwave background. The CMB has also taught us about the polarization of light, another subtle property that carries additional information. Light is an electromagnetic wave, and it can be polarized, meaning its electric field oscillates in a particular direction. The CMB is slightly polarized due to scattering off electrons at recombination, and the pattern of polarization across the sky provides independent confirmation of our models and additional constraints on cosmic parameters. There are two types of polarization patterns in the CMB, called E modes and B modes. E modes were detected years ago and are produced by the standard density fluctuations. B modes are more subtle and can be produced by gravitational waves from the inflationary epoch. Detecting primordial B modes would be a major discovery, providing direct evidence of inflation and potentially telling us about the energy scale at which inflation occurred. Several experiments are currently searching for this signal. As sleep draws near, let yourself marvel at the detective work involved in extracting all this information from the CMB. We're looking at light that has been traveling for over 13 billion years. We're measuring temperature differences of millionths of a degree. We're finding patterns in the noise, extracting signals buried in foregrounds from our own galaxy and instrument imperfections. And from all this, we're reconstructing the conditions of the universe when it was 380,000 years old, determining its composition, its age, its geometry, its history. The cosmic microwave background is the most important observational tool in cosmology. It's our baby picture of the universe, showing cosmic structure at its earliest observable moment. It's a time machine, allowing us to see back to an epoch long before stars or galaxies existed. It's a laboratory, where we can test our theories of the early universe against precise measurements. And it's a source of continued discovery, with future experiments promising to reveal even more subtle features and teach us even more about our cosmic origins. The story of the CMB, from its accidental discovery to its detailed mapping by sophisticated satellites, is also a testament to human curiosity and ingenuity. We built instruments sensitive enough to detect temperature variations of millionths of a degree. We launched them into space to escape the interfering signals from Earth. We developed mathematical tools to analyze the data and extract meaningful information. We constructed theoretical models to interpret what we found, and step by step, observation by observation, we built up a detailed picture of the early universe. When you look at an image of the CMB, those mottled patterns of slightly warmer and cooler regions, you're seeing quantum fluctuations made visible, the blueprint of cosmic structure, the face of the universe in its infancy. Every spot on that map corresponds to a real place, a region hundreds of millions of light years across. seen as it was more than 13 billion years ago. And here's something profound to contemplate. The CMB photons are still arriving. Right now, as you rest here, photons that have been traveling since recombination are passing through the space you occupy. You're constantly bathed in this ancient light, though your eyes can't detect it because it's been stretched into invisible microwave wavelengths. The cosmic microwave background isn't just a historical artifact. It's a present reality, filling space, carrying information from the edge of the observable universe. Future observations will continue to probe the CMB with ever greater precision. We'll search for those primordial B-mode polarization patterns that would reveal gravitational waves from inflation. We'll look for subtle distortions in the spectrum that might tell us about energy injection in the early universe. We'll map the polarization at smaller scales to learn about reionization and the first stars. Each new observation adds detail to our picture, refines our parameters, potentially reveals surprises that challenge our current understanding. The cosmic microwave background has transformed cosmology from a largely speculative field into a precision science. Before its discovery, theories about the early universe were difficult to test and often relied on philosophical arguments as much as observations. After its discovery, and especially after the detailed mapping by Kobe, WMAP, and Planck, we have hard data to confront our theories with. We can calculate predictions and check them against observations. We can measure the universe's properties and watch our models succeed or fail. The dawn of structure. How did nothing become something? Imagine a perfectly smooth ocean, its surface undisturbed by even the slightest ripple. Now imagine that over billions of years, this featureless expanse transforms into a magnificent landscape of islands and continents, mountains and valleys, rivers and coastlines. This is the journey the universe took, from the nearly uniform soup revealed by the cosmic microwave background to the rich tapestry of galaxies, clusters, and vast cosmic voids we observe today. It's a story of how the tiniest imperfections grew into grand structures, how gravity amplified whispers into symphonies, how nothing became something. As you settle into rest tonight, let's explore this transformation, the dawn of cosmic structure. When the universe evolved from boring uniformity into fascinating complexity, it's a story where dark matter plays the leading role, where the first stars ignited in the darkness, and where the seeds planted during inflation finally sprouted into the cosmic garden we inhabit. We left the universe at recombination, 380,000 years after the Big Bang, when it had just become transparent. The cosmic microwave background shows us this moment, revealing a universe that was remarkably smooth, with density variations of only 1 part in 100,000. These variations were tiny, but they were crucial. Without them, nothing interesting would ever have happened. The universe would have remained a uniform, boring gas of hydrogen and helium, expanding and cooling forever, never forming stars or galaxies or planets or life. But the variations existed, and they contained the potential for everything that would follow. The question is, how do such tiny irregularities grow into the spectacular structures we see today? The answer is gravity, that most patient and persistent of forces. Gravity is unique among the fundamental forces in that it's always attractive and it acts over infinite distances. Every piece of matter attracts every other piece of matter, and crucially, gravity has a positive feedback mechanism built into it. If a region is slightly denser than average, it has slightly more mass and therefore slightly stronger gravity. This stronger gravity attracts more matter from the surroundings, making the region even denser, which strengthens its gravity further, which attracts even more matter. Dense regions get denser while less dense regions become voids. This process is called gravitational instability, and it's the engine that drives structure formation in the universe. But there's a complication. In the early universe, ordinary matter, the atoms of hydrogen and helium, couldn't collapse freely under gravity. The matter was coupled to radiation, bathed in a sea of photons. If you tried to compress the gas, you'd also compress the radiation, which would increase the pressure and resist the compression. The radiation pressure acted like a cushion, preventing small-scale structures from collapsing. This is where dark matter enters the story, and it's impossible to overstate how important dark matter is to structure formation. Dark matter is mysterious. We don't know what it's made of. It doesn't emit, absorb, or scatter light, which is why it's dark. We've never detected a dark matter particle directly in a laboratory, but we know it exists because we can see its gravitational effects. Galaxies rotate too fast to be held together by the gravity of their visible matter alone. Galaxy clusters contain much more mass than we can account for from stars and gas. Gravitational lensing, the bending of light by mass, reveals dark matter's presence throughout the cosmos. And crucially for our story, dark matter doesn't interact with radiation. It doesn't feel radiation pressure. While ordinary matter was trapped in a tug-of-war between gravity trying to pull it together and radiation pressure pushing back, dark matter was free to collapse under its own gravity from the very beginning. Picture the universe after recombination. The ordinary matter, now neutral atoms, is distributed almost uniformly with tiny variations. The dark matter, which makes up about 85% of all matter in the universe, has the same tiny variations in density. But while ordinary matter is still coupled to radiation and slowly settling down, dark matter has already been collapsing for hundreds of thousands of years. In the regions where dark matter was slightly denser, it began forming clumps, dark matter halos, invisible concentrations of mass held together by their own gravity. These halos grew as they attracted more dark matter from their surroundings. The densest regions grew fastest, accumulating mass and deepening their gravitational wells. As you drift towards sleep, imagine these invisible structures forming throughout space, dark matter halos of various sizes, from masses smaller than modern galaxies to enormous concentrations that would become galaxy clusters. They were the skeleton upon which all visible structure would later form, the scaffolding of the cosmic web. Once the ordinary matter had decoupled from radiation at recombination, it began to feel the gravitational pull of these dark matter halos. The hydrogen and helium gas started flowing into the gravitational wells created by dark matter. Where dark matter was densest, ordinary matter accumulated. The gas fell inward, drawn by gravity, beginning to fill in the invisible structures that dark matter had outlined. This process happened at all scales simultaneously. Small dark matter, halos, with masses perhaps 1,000,000 times the mass of the Sun, formed first and began attracting gas. Larger halos, with masses of billions or trillions of solar masses, took longer to assemble. The small halos often merged together to form larger ones, building up structure hierarchically from the bottom up. By about 100 million years after the Big Bang, some of these gas clouds falling into dark matter halos had become dense and massive enough to begin the next crucial phase, the formation of the first stars. The first stars were nothing like the Sun or other stars we see today. They formed from pristine gas, pure hydrogen and helium with no heavier elements. This made them very different from modern stars, which form from gas enriched with elements like carbon, oxygen and iron produced by previous generations of stars. The reason this matters has to do with cooling. For a gas cloud to collapse and form a star, it needs to radiate away energy. If the cloud can't cool efficiently, the pressure from heating will prevent further collapse. Modern star-forming gas can cool very effectively because it contains molecules like carbon monoxide and dust grains that efficiently radiate away energy. But primordial gas, made only of hydrogen and helium, has very limited cooling mechanisms. It can form molecular hydrogen, which can radiate some energy, but not nearly as efficiently as the complex molecules available in enriched gas. This inefficient cooling meant that primordial gas clouds had to be much more massive before they could collapse to form stars. While typical stars forming today might have masses ranging from less than 1/10 the mass of the Sun to perhaps 100 solar masses, the first stars, called population 3 stars, were probably giants, with masses perhaps 100 to 1,000 times the mass of the Sun. These massive first stars would have been extraordinary objects. They would have burned incredibly hot, with surface temperatures far higher than ordinary stars. They would have shone with brilliant blue-white light, emitting enormous amounts of ultraviolet radiation, and they would have lived fast and died young, exhausting their nuclear fuel in just a few million years compared to the 10 billion year lifetime of a star like the Sun. The moment when the first star ignited, when nuclear fusion first began in its core and it started shining, was one of the most important moments in cosmic history. This was cosmic dawn, the end of the Dark Ages, the moment when the universe lit up after hundreds of millions of years of darkness. Where before there had been only the fading glow of the cosmic microwave background, now there were point sources of light, beacons shining in the primordial darkness. These first stars had profound effects on their surroundings. Their intense ultraviolet radiation began ionizing the hydrogen gas around them, creating bubbles of ionized plasma expanding outward from each star. This was the beginning of reionization, the process that would eventually transform the neutral universe back into an ionized one, though now in a very different configuration than the uniform plasma that existed before recombination. The first stars also began the process of chemical enrichment. In their cores, nuclear fusion converted hydrogen into helium and then into heavier elements: carbon, oxygen, silicon, iron. When these massive stars exhausted their fuel and exploded as supernovae, they scattered these newly forged elements into the surrounding gas. For the first time, the universe contained elements beyond hydrogen and helium. These elements would be incorporated into the next generation of stars, allowing smaller stars to form and beginning the gradual enrichment of the cosmos that would eventually make planets and life possible. Let's think about the timeline of these events as you rest here in the quiet darkness. At 380,000 years, recombination occurred and the universe became transparent. From then until about 150 million years was the Dark Ages, when dark matter was collapsing into halos and gas was flowing inward, but no stars had yet formed. Around 150 million to 200 million years after the Big Bang, the first stars ignited, ending the Dark Ages and beginning cosmic dawn. Over the next few hundred million years, more and more stars formed, and they began clustering together in the first proto-galaxies. These first proto-galaxies were not like the grand spiral and elliptical galaxies we see today. They were small, irregular collections of stars and gas, perhaps containing only a few million stars compared to hundreds of billions in a large modern galaxy. But they were the building blocks from which larger galaxies would form through mergers and accretion. The process of galaxy formation is hierarchical. Small proto-galaxies formed first within small dark matter halos. These proto-galaxies would then merge together, combining their stars and gas and dark matter into larger structures. Multiple small galaxies could merge to form a larger one. Those larger galaxies could merge with others to form even larger ones. This hierarchical assembly continues today. Our own Milky Way is currently in the process of consuming several smaller satellite galaxies, and in a few billion years, it will merge with the Andromeda Galaxy to form an even larger elliptical galaxy. Dark matter continued to play the crucial role throughout this process. The visible galaxies we see are really just the bright centers of much larger dark matter halos. These halos extend far beyond the visible matter, forming vast invisible structures. When galaxies merge, it's really the dark matter halos that are merging first, with the visible matter following along. As structure grew, the universe developed what we now call the cosmic web. This is the large-scale structure of matter distribution, visible when we map the locations of galaxies across vast volumes of space. The cosmic web consists of several distinct features: dense clusters where many galaxies gather together, drawn by their combined gravity; filaments, elongated structures where galaxies line up along threads of dark matter; sheets or walls, flattened regions where galaxies accumulate; and voids, vast empty regions where few galaxies exist. This web-like structure emerged naturally from gravitational instability acting on the initial density fluctuations. The fluctuations weren't random noise. They had structure at different scales, and as gravity amplified them, this structure manifested as the cosmic web. Computer simulations of structure formation, which follow the gravitational evolution of billions of particles representing dark matter and gas, reproduce the cosmic web remarkably well, matching what we observe in the real universe. The formation of the first stars and galaxies also left imprints that we can observe today. The process of reionization, driven by ultraviolet light from early stars and possibly early black holes, transformed the universe from neutral to ionized over several 100 million years. This transformation left subtle signatures in the cosmic microwave background, slight changes in the polarization of the light caused by the CMB photons scattering off electrons during reionization. Modern CMB experiments can detect these signatures and constrain when and how reionization occurred. Can also observe some of the earliest galaxies directly using powerful telescopes, like the James Webb Space Telescope. When we look at very distant objects, we're seeing them as they were long ago, because light takes time to travel across space. The most distant galaxies we've observed appear as they were less than 1 billion years after the Big Bang, when they were just forming. These young galaxies look different from modern ones, smaller, more irregular, often vigorously forming stars. By studying them, we can watch the process of galaxy formation in action. As sleep approaches, consider the remarkable transformation the universe underwent during this epoch. From the nearly featureless state revealed by the cosmic microwave background, from those tiny variations of 1 part in 100,000, grew all the rich structure we observe today. Galaxies containing hundreds of billions of stars, galaxy clusters containing thousands of galaxies, the vast cosmic web stretching across billions of light years. All of this complexity, all of this structure, emerged from almost nothing, from the tiniest quantum fluctuations inflated to cosmic scales, amplified by gravity over billions of years. And at the heart of this process was dark matter, the invisible component that makes up most of the matter in the universe. Without dark matter, structure formation would have proceeded too slowly. The universe would still be mostly smooth and featureless, with only the beginnings of structure emerging. Stars and galaxies as we know them would not exist. Dark matter provided the gravitational framework, the invisible scaffolding, upon which visible structure could form. The first stars played their crucial role as well, igniting in the darkness, enriching the universe with heavy elements, ionizing the hydrogen gas, and clustering together into the first galaxies. They were pioneers, explorers of the darkness, transforming the universe from a simple mixture of hydrogen and helium into a chemically complex cosmos, where eventually planets could form and life could emerge. This process of structure formation is ongoing. The universe continues to evolve, galaxies continue to merge, stars continue to form and die, the cosmic web continues to develop, with matter flowing along filaments toward clusters, while voids grow larger and emptier. The universe is dynamic, constantly changing, though on timescales so long that they're imperceptible to human observers. When you look up at the night sky, at the stars and the faint smudge of the Milky Way, you're seeing the end result of this process. Every star is part of a galaxy that formed through the merger of smaller protogalaxies that formed from gas falling into dark matter halos that grew from tiny density fluctuations in the early universe. Every structure has a history stretching back to the beginning, a lineage that can be traced through billions of years of cosmic evolution. The universe solved a remarkable problem: how to get from almost nothing to something, from tiny variations to grand structures, from featureless uniformity to rich complexity. The solution involved dark matter, providing the framework, gravity providing the force, and time providing the canvas. Simple physical laws, acting on simple initial conditions, generated all the complexity we see, and we can understand this process. Through observations, simulations, and theoretical calculations, we've reconstructed how structure formed. We can match our models to observations, adjust parameters, test predictions. We can watch simulated universes evolve in computers and see them develop cosmic webs that look remarkably like the real universe. We can observe young galaxies billions of light years away and see them in states that match our predictions for that cosmic epoch. Ionization. How did the universe become transparent? Again, imagine a darkened theater where someone begins lighting candles, one by one. At first, just a single flickering flame pierces the darkness, creating a small bubble of light in the surrounding gloom. Then another candle is lit, and another, each creating its own sphere of illumination. Gradually, these bubbles of light expand and merge, touching and overlapping, until eventually the entire theater is filled with light and the darkness has been banished. This is the story of reionization, one of the great phase transitions in cosmic history, when the first stars and galaxies transformed the universe from a dark, neutral state back into an ionized, transparent one. As you settle into rest tonight, let's explore this dramatic epoch from roughly 150 million to 1 billion years after the Big Bang, when the universe underwent its second great transformation in the state of matter. It's a story still being written, a frontier of cosmological research where new telescopes are revealing the details of how the cosmic dark ages ended and the universe as we know it today came into being. We need to start by clarifying something that might seem confusing. Didn't we say the universe became transparent at recombination? Yes, we did, but transparency and ionization are not the same thing, and understanding this difference is crucial to understanding reionization. At recombination, 380,000 years after the Big Bang, electrons combined with nuclei to form neutral atoms. This made the universe transparent because neutral atoms don't scatter light nearly as effectively as free electrons do. Light could suddenly travel freely through space. The universe became transparent while simultaneously becoming neutral. During reionization, something different happened. The intense radiation from the first stars and galaxies stripped electrons back off those neutral atoms, ionizing the hydrogen gas throughout the universe. The universe became ionized again, returning to a plasma state, but it remained transparent. How is this possible? The key is density. Before recombination, the universe was dense enough that even though light could travel, it didn't get very far before scattering off a free electron. After recombination and through reionization, even though hydrogen became ionized again, the universe had expanded so much that the free electrons were far too sparse to effectively scatter light. You could have an ionized universe that's still transparent, as long as it's diffuse enough, which is exactly what happened. So reionization didn't make the universe opaque again. Instead, it transformed the chemical state of the intergalactic medium, the thin gas between galaxies, from neutral hydrogen atoms back into ionized hydrogen plasma, while maintaining the transparency that had existed since recombination. Let's trace the timeline of this transformation. After recombination, the universe was filled with neutral hydrogen and helium gas with tiny density variations. This gas began flowing into the gravitational wells created by dark matter halos. In the densest regions, the gas accumulated and cooled and eventually collapsed to form the first stars. This process took time, roughly 100 to 200 million years, before conditions were right for the first stars to ignite. When those first massive population 3 stars finally lit up, they were extraordinarily luminous sources of ultraviolet radiation. These stars were so hot that much of their light was emitted at wavelengths short enough to ionize hydrogen. An ultraviolet photon with enough energy can strike a hydrogen atom and knock its electron free, ionizing the atom. The photon is absorbed in the process, its energy going into separating the electron from the nucleus. Around each of these first stars, a bubble of ionized hydrogen began to form and grow. The star emitted UV photons in all directions. These photons traveled outward through the neutral hydrogen gas, ionizing atoms as they went. The ionization front, the boundary between ionized and neutral gas, expanded outward from the star at speeds approaching the speed of light. But here's something important. The ionized bubbles didn't just keep expanding forever. They reached a certain size and then stopped growing, or grew much more slowly. Why? Because the universe is not empty. Even in the diffuse intergalactic medium, there are electrons and protons. In the ionized regions, these free electrons and protons constantly collide with each other and recombine, forming neutral atoms again. This process is called recombination, the same name as the earlier epoch, but it's happening continuously now at a low rate. An equilibrium is established. The star produces ionizing photons that ionize atoms in the surrounding gas. But those atoms don't stay ionized forever. They recombine at some rate. The ionized bubble grows until the rate of new ionizations equals the rate of recombinations, and then it stabilizes at a certain size. More powerful sources create larger bubbles. Weaker sources create smaller ones. As you drift towards sleep, picture the universe during early reionization, perhaps 200 million years after the Big Bang. Scattered throughout space are these isolated bubbles of ionized gas surrounding the first stars and small protogalaxies. Between the bubbles, the intergalactic medium remains neutral, still in the dark ages. The universe is a patchwork, a mix of ionized regions and neutral regions, like Swiss cheese with the holes representing the ionized bubbles. As time passes, more and more stars form. More bubbles appear. Existing bubbles grow as the sources within them continue emitting ionizing radiation. Small protogalaxies merge to form larger ones with more stars, and therefore more ionizing power. The bubbles begin to overlap and merge. When two ionized bubbles touch, they combine into a single larger bubble. This process accelerates over time through a positive feedback mechanism. Once a significant fraction of the universe is ionized, the remaining neutral gas becomes easier to ionize because there's less neutral material to absorb the ionizing photons. The photons can travel farther before being absorbed, ionizing more distant regions. Reionization, which starts slowly, accelerates as it progresses, eventually sweeping through the last neutral regions in a cosmic phase transition. By approximately 1 billion years after the Big Bang, the process was essentially complete. The intergalactic medium throughout the observable universe had been transformed from neutral hydrogen into ionized hydrogen. The last bubbles had merged. The last neutral regions had been ionized. The universe had returned to an ionized state, though vastly more diffuse than the dense plasma that existed before recombination. But saying ionization was complete by 1 billion years is a simplification. The process wasn't instantaneous or perfectly uniform. Some regions were ionized earlier, others later. Dense regions with many stars were ionized first. Voids with few sources remained neutral longer. There was structure to the ionization process, a complex pattern of ionized and neutral regions evolving over hundreds of millions of years. Understanding the details of this process is one of the major goals of modern observational cosmology. When exactly did ionization begin? How long did it take? What were the sources of ionizing photons? Was it mainly stars, or did early black holes contribute significantly? How did the process vary from region to region? These questions are difficult to answer because ionization happened long ago, at enormous distances. The light we're receiving now from that epoch has been traveling for more than 13 billion years. The galaxies that caused ionization are faint, distant, and challenging to observe, even with our most powerful telescopes. But astronomers have developed clever ways to study ionization. One of the most important involves observing distant quasars. Quasars are extremely luminous objects powered by supermassive black holes actively consuming matter. The most distant quasars we can see appear as they were less than 1 billion years after the Big Bang, during or just after reionization. When we observe the spectrum of a distant quasar, the light it emits, we see absorption lines where intervening gas between us and the quasar has absorbed specific wavelengths. Neutral hydrogen absorbs light at a characteristic wavelength called Lyman alpha. If there's neutral hydrogen between us and the quasar, we see absorption at this wavelength. For quasars at moderate distances, we see a forest of these absorption lines, the Lyman alpha forest, each line corresponding to a cloud of neutral hydrogen at a different distance along the line of sight. But for the most distant quasars, those seen as they were during reionization, something dramatic happens. The Lyman alpha absorption becomes complete. All light at wavelengths corresponding to neutral hydrogen is completely absorbed. The spectrum goes dark at these wavelengths, a feature called the Gunn-Peterson trough. This complete absorption tells us that there was significant neutral hydrogen in the intergalactic medium along the line of sight to these distant quasars. The universe was not yet fully ionized. By observing quasars at different distances, corresponding to different cosmic times, we can map out when ionization occurred and how much neutral hydrogen existed at different epochs. Another powerful technique involves studying the cosmic microwave background. The CMB photons, traveling from the surface of last scattering toward us, pass through the entire history of the universe. When ionization occurred and free electrons appeared in the intergalactic medium, some CMB photons scattered off these electrons. This scattering left a subtle imprint in the polarization of the CMB, a signature that modern CMB experiments can detect. By measuring this signal, we can determine when ionization occurred and how much of the universe was ionized at different times. The most exciting recent developments in studying ionization come from the James Webb Space Telescope, JWST, which began operations in 2022. JWST was specifically designed to observe the earliest galaxies, the sources responsible for ionization. With its large mirror and sensitive infrared detectors, JWST can see galaxies as they were less than 1 billion years after the Big Bang. During the ionization epoch, what JWST has found is remarkable and somewhat surprising. The early universe was more active, more full of galaxies than many models predicted. Galaxies formed earlier and were more abundant than expected. Some of these early galaxies are surprisingly bright and massive, challenging our understanding of how quickly structure could form and how efficiently early galaxies could produce stars. These observations are still being analyzed and debated. Do we need to revise our models of galaxy formation? Are there more efficient ways to form stars in the early universe than we thought? Did the first stars form even earlier than we believed? These are open questions at the frontier of the field. As you lie here in the darkness, consider what the sources of ionization actually were. The obvious answer is stars, particularly the massive hot population 3 stars and the somewhat less massive population 2 stars that followed. These stars emit copious ultraviolet radiation capable of ionizing hydrogen. But there may have been other important contributors. Early black holes, particularly supermassive black holes in the centers of young galaxies, can be extremely luminous sources of ionizing radiation. As matter spirals into a black hole, it heats up and emits radiation across the spectrum, including plenty of UV photons. Some models suggest that black holes contributed significantly to ionization, perhaps ionizing a substantial fraction of the intergalactic medium. There's also the question of escape fraction. Not all the ionizing photons produced by stars necessarily escape from their host galaxies to ionize the intergalactic medium. Many are absorbed by gas and dust within the galaxy itself. The escape fraction is the percentage of ionizing photons that make it out of galaxies into intergalactic space. This number is crucial for understanding ionization, but difficult to measure directly, especially for the earliest galaxies. Recent JWST observations suggest that early galaxies may have had higher escape fractions than typical galaxies today, perhaps because they were less chemically enriched and had less dust to absorb UV photons, or because feedback from stars and supernovae created channels through which radiation could escape more easily. The topology of ionization, the spatial pattern of ionized and neutral regions, also carries important information. Computer simulations can predict what this pattern should look like, given different assumptions about the sources and timing of ionization. These simulations show that ionization should proceed inside out, with dense regions ionizing first and voids ionizing last. The ionized bubbles should have characteristic sizes depending on the distribution and luminosity of sources. Observationally, we're beginning to map this topology using a technique called 21 centimeter mapping. Neutral hydrogen emits radio waves at a wavelength of 21 centimeters due to a quantum transition in the hydrogen atom. By mapping the distribution of this emission from the epoch of ionization, we can see which regions were still neutral and which were ionized at different times. Several radio telescope arrays around the world are attempting this difficult observation, trying to detect the faint signal from neutral hydrogen during reionization. The challenge is enormous. The signal from the reionization epoch is incredibly faint, buried under much stronger foreground emission from our own galaxy and other sources. But if successful, 21 centimeter mapping would provide a three-dimensional picture of reionization, showing how the ionized bubbles formed, grew, and merged over time. Reionization represents a fundamental transformation in the state of the universe. Before reionization, the intergalactic medium was cold, neutral, and in some sense dormant. After reionization, it became hot, ionized, and more dynamic. This change affected many aspects of cosmic evolution. For instance, reionization made it harder for small galaxies to form. The process of ionizing the intergalactic medium heated it up, increasing the gas pressure. This pressure makes it harder for gas to fall into small dark matter halos and form stars. Reionization may have suppressed the formation of dwarf galaxies, which is relevant for understanding the population of satellite galaxies around the Milky Way and other large galaxies. Reionization also established the thermal state of the intergalactic medium that persists to some degree today. The ionized gas is heated by the ionizing radiation to temperatures of around 10,000 to 20,000 degrees. This hot ionized plasma filling the space between galaxies is sometimes called the warm-hot intergalactic medium, and it contains a significant fraction of the ordinary matter in the universe. As sleep draws near, reflect on the dramatic nature of this transformation. Within a few 100 million years, the character of the universe changed completely. What had been a dark, cold, neutral cosmos became an illuminated, hot, ionized one. Every cubic meter of intergalactic space was transformed by radiation from distant sources, photons that had traveled for millions of years to reach and ionize that particular location. This transformation was driven by structure formation, by the first stars and galaxies that emerged from the Dark Ages. It represents the universe coming alive, becoming active, full of sources of energy and light. Before reionization, the universe was passive, coasting along in the dark. After reionization, it was dynamic, filled with stars and galaxies, radiation and motion. The epoch of reionization also represents a transition in our observational capabilities. We can see galaxies and quasars from after reionization relatively easily, their light traveling unimpeded to our telescopes. But observing the universe during reionization is much harder because the neutral hydrogen absorbs certain wavelengths of light. And observing the universe before reionization, during the Dark Ages when no stars had formed, is almost impossible with conventional telescopes because there are no sources of visible light to observe. This makes reionization a kind of observational horizon. With current technology, we can see back to near the end of reionization. JWST is pushing this boundary, observing galaxies from earlier and earlier in the reionization epoch. Future telescopes may push further still, perhaps observing some of the very first population 3 stars that began the process. But much of the Dark Ages, the period from recombination to the formation of the first stars, remains hidden from direct observation. We can infer what happened during this period through theory and simulation, and we can see its effects in the cosmic microwave background and in the first galaxies. But we cannot yet directly observe it. Reionization connects different epochs of cosmic history. It links the Dark Ages to the universe of galaxies we observe today. It bridges the gap between the simple, structureless universe of recombination and the complex, highly structured universe of the present. Understanding reionization is crucial for understanding cosmic evolution as a whole. The universe's growth spurt. How did galaxies and clusters assemble? Imagine watching a time-lapse video of a city growing over centuries. At first, there are scattered small villages, isolated settlements separated by wilderness. Gradually, these villages expand, some merging together, forming towns. The towns grow into cities, and cities connect through roads and highways, forming a vast interconnected network. This is remarkably similar to how the universe developed its structure, how the first small proto-galaxies merged and grew into the magnificent galaxies we see today, and how those galaxies gathered into clusters and superclusters, forming the grand cosmic web that spans billions of light years. As you settle into rest tonight, let's explore the universe's growth spurt, the billions of years from the end of reionization to the present day, when structure assembled itself hierarchically, when galaxies evolved from small, irregular collections of stars into grand spirals and ellipticals, when the cosmic web emerged in all its glory. It's a story of mergers and collisions, of growth and transformation, of simple structures becoming complex ones through the patient work of gravity over cosmic time. We left the universe at about 1 billion years after the Big Bang, when reionization was largely complete and the first generation of small proto-galaxies had formed. These early galaxies were nothing like the Milky Way or Andromeda today. They were small, perhaps containing only millions to hundreds of millions of stars rather than hundreds of billions. They were irregular in shape, lacking the organized structure of spiral arms or the smooth distribution of elliptical galaxies. They were vigorously forming stars, converting their gas into stars at rates much higher than typical galaxies today. These small galaxies were just the beginning. The universe was about to undergo a long period of assembly, where structure would build up hierarchically from small to large. This hierarchical structure formation is a fundamental prediction of our cosmological models, emerging naturally from gravitational growth of the initial density fluctuations in the presence of dark matter. The basic principle is simple. Small structures form first because they require lower densities to collapse, and they take less time to assemble. Once formed, these small structures attract each other gravitationally. They fall toward each other, orbit around each other, and eventually merge together, combining their stars, gas, and dark matter into a larger structure. This larger structure can then merge with other similar-sized structures or accrete smaller ones, growing still larger. The process continues, building up structure from the bottom up, from small to large. Over billions of years, picture 2 small proto-galaxies, each containing perhaps 10 million stars, orbiting within the same large dark matter halo. Gravity draws them together over millions of years. Their orbits decay as they interact. Eventually they collide and merge, their stars intermingling, their gas clouds colliding and triggering bursts of new star formation, their dark matter halos combining. The result is a single galaxy with perhaps 20 million stars, more massive than either progenitor. This merged galaxy then encounters another galaxy of similar mass. Again, gravity brings them together. Again, they merge. The process repeats, each merger adding mass and complexity. Over billions of years, through dozens or hundreds of mergers and continuous accretion of smaller satellites, a galaxy like the Milky Way can be assembled. we have strong evidence that this hierarchical assembly actually occurs. When we look at distant galaxies, seeing them as they were billions of years ago, we see more mergers in progress than we do in the nearby universe. Young galaxies more often have disturbed, irregular shapes indicating recent interactions. We see tidal streams, bridges of stars connecting interacting galaxies, and long tails extending from galaxies that have experienced close encounters. We can also see the history of mergers recorded in the structure of galaxies today. The Milky Way, our home galaxy, contains streams of stars in its outer regions, remnants of small satellite galaxies it has consumed. These streams trace the orbits of the disrupted satellites, providing a fossil record of past mergers. By mapping these streams, we can reconstruct which satellite galaxies merged with the Milky Way and approximately when those mergers occurred. As you drift towards sleep, consider that the Milky Way itself is in the process of consuming several small satellite galaxies right now. The Sagittarius dwarf galaxy is being torn apart by the Milky Way's gravity, leaving a stream of stars wrapped around our galaxy. The large and small Magellanic Clouds, visible from the southern hemisphere, are satellite galaxies that will eventually merge with the Milky Way. And in about 4 billion years, the Milky Way will experience its most dramatic merger yet, colliding and combining with the Andromeda Galaxy to form a single, larger elliptical galaxy. Computer simulations have been crucial for understanding hierarchical assembly. In these simulations, cosmologists start with initial conditions matching the density fluctuations we observe in the cosmic microwave background. They then let gravity evolve these fluctuations forward in time, calculating how billions of dark matter particles move and cluster under their mutual gravitational attraction. They include the physics of gas cooling, star formation, supernova feedback, and black hole growth. The result is a simulated universe that can be directly compared to observations. These simulations reproduce the hierarchical assembly process beautifully. They show small dark matter halos forming first, accreting gas and forming protogalaxies. They show these protogalaxies merging hierarchically to form larger galaxies. They show galaxies gathering into groups and clusters. They show the emergence of the cosmic web, with galaxies arranged along filaments connecting dense clusters, surrounding vast empty voids. The simulated universe looks remarkably like the real one, confirming that we understand the basic physics of structure formation. But galaxy evolution involves more than just mergers. Internal processes within galaxies also drive their evolution and shape their properties. One of the most important of these is the role of supermassive black holes. Nearly every large galaxy contains a supermassive black hole at its center, with masses ranging from millions to billions of times the mass of the Sun. Our own Milky Way has a supermassive black hole called Sagittarius, a star. With a mass of about 4 million solar masses, the origin of these black holes is still debated. They may have grown from the remnants of the first population 3 stars, or they may have formed through direct collapse of gas clouds in the early universe, or both processes may have contributed. What's clear is that these supermassive black holes play a crucial role in galaxy evolution through a process called AGN feedback, where AGN stands for active galactic nucleus. When gas falls toward a supermassive black hole, it forms an accretion disk, spiraling inward and heating up through friction. This process is extraordinarily efficient at converting gravitational potential energy into radiation. Before gas actually crosses the event horizon and disappears into the black hole, it can radiate away a significant fraction of its rest mass energy. An actively feeding supermassive black hole can therefore be extremely luminous, outshining all the stars in its host galaxy combined. This is what we observe as quasars, the most luminous persistent sources in the universe. But this luminosity has consequences. The intense radiation and powerful jets of particles launched by the black hole can heat the surrounding gas, blow it out of the galaxy, or prevent it from cooling and forming stars. This feedback from supermassive black holes helps explain why the most massive galaxies in the universe have stopped forming stars. Without AGN feedback, simulations predict that massive galaxies should continue accreting gas and forming stars at high rates. But observations show that the most massive galaxies are red and dead, containing old stellar populations with little ongoing star formation. The supermassive black holes in these galaxies appear to have quenched star formation by heating or expelling the gas that would otherwise form new stars. There's a remarkable correlation between the mass of a galaxy's supermassive black hole and the properties of its central bulge, the dense concentration of stars in the galaxy's center. More massive bulges contain more massive black holes, following a tight relationship. This suggests a deep connection between black hole growth and galaxy evolution, with the two processes regulating each other through feedback. Let's zoom out now from individual galaxies to larger scales. Galaxies don't exist in isolation. They gather together in groups and clusters, bound by their mutual gravity. The Milky Way is part of the Local Group, a collection of about 50 galaxies dominated by the Milky Way and Andromeda, with many smaller dwarf galaxies orbiting around these two giants. Larger galaxy clusters can contain hundreds or thousands of galaxies, all orbiting within a shared gravitational potential well. The Virgo cluster, the nearest large cluster to us, contains over 1,000 galaxies. The Coma cluster, one of the richest clusters known, contains thousands of galaxies. These clusters are massive structures, with total masses of 10 to the power of 14 or 10 to the power of 15 solar masses, most of that mass in the form of dark matter. Galaxy clusters form through hierarchical assembly, just like galaxies themselves. Small groups of galaxies merge to form larger groups. Groups merge to form clusters, and clusters themselves can merge to form even larger structures. When clusters merge, the collisions are spectacular events. The galaxies themselves usually don't collide directly because there's so much empty space within each cluster. But the hot gas between galaxies, the intra-cluster medium, does collide, creating shock waves and heating the gas to temperatures of tens of millions of degrees. We can observe these cluster mergers through X-ray telescopes, which detect the hot intra-cluster gas. The Bullet cluster is a famous example, showing two galaxy clusters that have passed through each other. X-ray observations show the hot gas from each cluster, now separated and trailing behind. But observations of gravitational lensing, the bending of light by mass, show that most of the mass in each cluster, the dark matter, passed right through without slowing down. This provides dramatic visual evidence for dark matter's existence, separating its location from the location of the normal matter. As you rest here, imagine the vast scales we're talking about. A galaxy might be 100,000 light-years across. A galaxy cluster might be 10 million light-years across. The structures we're about to discuss, the cosmic web, extends across billions of light-years, encompassing the entire observable universe. The cosmic web is the largest scale structure in the universe, and it's one of the most beautiful patterns nature has created. When astronomers map the positions of millions of galaxies across vast volumes of space, they find that galaxies are not randomly distributed. Instead, they're arranged in a distinct pattern, dense clusters connected by elongated filaments, surrounding vast empty regions called voids. The cosmic web emerges naturally from gravitational instability. The initial density fluctuations from inflation weren't uniform in all directions. Some regions were overdense along certain directions, creating sheet-like or filamentary patterns. As these overdensities collapsed under gravity, they maintained their elongated shapes. Matter flows along filaments toward the nodes where filaments intersect, and at these nodes, galaxy clusters form. Voids form in the regions that were initially slightly underdense. As matter flows out of these regions toward the overdense filaments and clusters, the voids become more empty, growing larger over time. The universe develops a sponge-like structure, with matter concentrated in a network of filaments and sheets surrounding roughly spherical voids. The cosmic web can be visualized through galaxy redshift surveys, where astronomers measure the distance to millions of galaxies and map their three-dimensional distribution. The Sloan Digital Sky Survey, one of the most ambitious astronomical surveys ever conducted, has mapped the positions of hundreds of millions of galaxies, revealing the cosmic web in exquisite detail. The maps look like biological structures, like neural networks or the circulatory system, with galaxies tracing out an intricate web of light against the darkness of the voids. The filaments in the cosmic web are not empty. They contain diffuse gas, mostly hydrogen, that's difficult to observe directly, but reveals itself through absorption lines in the spectra of distant quasars. This is the Lyman alpha forest we mentioned earlier, each absorption line corresponding to a filament or cloud of gas along the line of sight. By studying these absorption features, astronomers can map the distribution of gas in the cosmic web and understand how matter is distributed throughout intergalactic space. The cosmic web is also shaped by dark energy. that mysterious component making up about 68% of the universe's energy content. Dark energy acts like a negative pressure, accelerating the expansion of the universe. This acceleration affects structure formation, particularly at the largest scales. It slows down the growth of structure by making space expand faster, fighting against gravity's tendency to pull matter together. The discovery of dark energy through observations of distant supernovae in the late 1990s was one of the most surprising findings in cosmology. It tells us that the universe's expansion is accelerating, not decelerating as most physicists expected. This acceleration is relatively recent in cosmic history, beginning when the universe was about half its current age, around 7 billion years ago. Before that, when matter and dark matter were denser, gravity was winning and the expansion was decelerating. After that point, as the universe expanded and matter became more dilute, dark energy became dominant and the expansion began accelerating. This acceleration has implications for the future. Structure formation is slowing down and will eventually stop. Galaxy clusters that are not yet gravitationally bound will never collapse because the accelerating expansion will pull them apart faster than gravity can bring them together. The cosmic web we see today represents roughly the final state of structure in the universe. New structures will continue to form within regions that are already gravitationally bound, but the largest scale structure is largely frozen in place by dark energy. As sleep approaches, consider the remarkable journey of structure formation from the first tiny fluctuations to the cosmic web today. Quantum fluctuations during inflation created variations of 1 part in 10 to the power of 5 in the density of matter. These variations grew under gravity, amplified by factors of millions, eventually producing the structures we observe today, with density contrasts of hundreds or thousands compared to the average cosmic density. Small protogalaxies formed first, containing millions of stars. They merged hierarchically, building up larger galaxies over billions of years. The Milky Way, with its 200 to 400 billion stars, assembled through hundreds of mergers and continuous accretion of smaller satellites. Supermassive black holes grew alongside galaxies, regulating their evolution through feedback. Galaxies gathered into groups and clusters gathered along filaments, forming the cosmic web that fills the universe with structure on the largest observable scales. This process was enabled by dark matter, which provided the gravitational scaffolding upon which visible structure could form. It was shaped by dark energy, which accelerated the expansion and set a limit on how large structures could grow. It was enriched by successive generations of stars, which produced heavier elements through nuclear fusion and scattered them through space in supernova explosions, gradually increasing the chemical complexity of the universe, and it continues today. The universe is still evolving, still forming structure, still experiencing mergers and interactions. The Milky Way is still accreting satellites. Galaxy clusters are still forming through the merger of smaller groups. The cosmic web is still developing, though more slowly now under the influence of dark energy. When you look up at the night sky, you're seeing the result of this cosmic growth spurt, this billions of years-long process of hierarchical structure formation. The Milky Way stretched across the sky as one galaxy among billions, itself a product of countless mergers. The fuzzy patch of the Andromeda Galaxy is another massive spiral, assembled through similar processes, destined to merge with the Milky Way in the distant future. The faint smudges of more distant galaxies, visible through telescopes, are participants in the cosmic web, connected through filaments of dark matter and gas to the vast network of structure filling the universe. The legacy of the first moments. How does the infant universe define our reality today? Imagine discovering that everything about your life today, your personality, your circumstances, your possibilities, was determined by events that happened in the first few moments after you were born. In a profound sense, this is true for the entire universe. The cosmos we inhabit today, with all its galaxies and stars, its structure and complexity, its very capacity to harbor life and consciousness, was shaped irreversibly by what happened in the first fraction of a second after the Big Bang. Those initial moments cast a long shadow across billions of years, defining the fundamental character of reality itself. As you settle into rest tonight, let's bring our journey full circle, connecting the infant universe we've explored to the cosmos we experience today. Let's trace how the first moments determined everything that followed, examine the deep mysteries that remain, and reflect on what it means to understand our cosmic origins. This is where physics meets philosophy, where the story of the universe becomes inseparable from the story of how we came to understand it. Let's start by listing what was determined in those first moments. In the first tiny fraction of a second during inflation, the expansion rate of the universe was set, space was flattened, and quantum fluctuations were stretched to cosmic scales, creating the seeds of all future structure. These fluctuations, variations of 1 part in 100,000, weren't random noise. They had specific statistical properties determined by the physics of inflation, properties we can still measure today in the cosmic microwave background. Without inflation, or something like it, the universe would have very different large-scale properties. It might be highly curved rather than flat. Different regions might have different physical properties, different temperatures, different expansion rates, because they would never have been in causal contact. The fluctuations that seeded structure might have the wrong amplitude or the wrong distribution of scales. The universe might be far too smooth to form galaxies, or so lumpy that it would have collapsed into black holes long ago. In the first microsecond, as the quark-gluon plasma transitioned into protons and neutrons, the ratio of these particles was established. The slight excess of matter over antimatter, that 1 in a billion asymmetry we discussed, was created through processes we still don't fully understand. Without this asymmetry, the universe today would contain only photons, the remnants of total matter, antimatter annihilation. No atoms, no chemistry, no stars, no planets, no life. Everything you see around you, every atom in your body, exists because of that primordial asymmetry. In the first few minutes, during Big Bang nucleosynthesis, the relative abundances of the lightest elements were established. 75% hydrogen, 25% helium, with traces of deuterium and lithium. This ratio has persisted for over 13 billion years. It determines the fuel available for stars, which in turn determines how stars evolve and what elements they produce. If the helium abundance was significantly different, stellar evolution would proceed differently, potentially making stars like the Sun impossible, or changing the types of heavy elements produced in supernovae. At 380,000 years, during recombination, the universe became transparent and the cosmic microwave background was released. This event created the oldest light we can observe and established the fundamental horizon of visibility. Everything we can ever see with light traces back to this moment or later. The universe before recombination is hidden behind this wall of light, accessible only through indirect means or non-electromagnetic messengers like gravitational waves or neutrinos. And over the following billions of years, through hierarchical structure formation, the universe assembled the galaxies and clusters we see today. But the pattern of this assembly, the locations and sizes of structures, the cosmic web itself, all trace back to those initial quantum fluctuations from inflation, amplified by billions of years of gravitational growth as you drift towards sleep. Consider how deterministic this process is. Given the initial conditions set in the first moments, the subsequent evolution of the universe follows from the laws of physics with remarkable inevitability. The density fluctuations had to grow into galaxies. The galaxies had to gather into clusters. The cosmic web had to form. These weren't random accidents, but necessary consequences of gravity acting on the initial conditions over cosmic time. Yet within this determinism, there's room for contingency. The exact details of when and where particular galaxies formed, which protogalaxies merged with which others, the specific history of our own Milky Way, these depend on details that are effectively random from our perspective. The universe is deterministic in its large-scale statistical properties, but unpredictable in its specific details. This brings us to one of the most profound questions we can ask. Could the universe have been different? Could the initial conditions have been different? And if so, would any other set of initial conditions have led to a universe capable of supporting complexity and life? These questions touch on what's called fine-tuning, the observation that many of the fundamental parameters of physics appear to be finely tuned to allow for complex structures and life. If the matter-antimatter asymmetry were much smaller, not enough matter would have survived annihilation. If it were much larger, the universe might have different properties. If the amplitude of the primordial fluctuations were much smaller, structures wouldn't have formed. If it were much larger, the universe might have fragmented into black holes. Similarly, many of the fundamental constants of nature appear finely tuned. If the strength of the strong nuclear force was slightly different, stable nuclei might not exist. If the electromagnetic force were different, Atoms would have different properties, and chemistry would work differently. If the cosmological constant related to dark energy were much larger, the universe would have expanded too rapidly for structures to form. Some physicists argue that this fine-tuning is evidence that our universe is one of many, perhaps infinitely many, in a vast multiverse where different regions have different physical laws and constants. In such a multiverse, most universes would be sterile, unable to support complexity or life. We find ourselves in one of the rare universes where the parameters happen to be right because we couldn't exist anywhere else. This is the anthropic principle, the observation that the universe must be compatible with the conscious life that observes it. Others argue that the apparent fine-tuning might be explained by deeper physics we don't yet understand, by fundamental principles that necessarily lead to these particular values of constants and initial conditions. Perhaps there's only one consistent set of physical laws, and they necessarily produce universes like ours. These are deep questions without clear answers, residing at the boundary between physics and philosophy. But they illustrate how understanding our cosmic origins forces us to confront fundamental questions about existence, necessity, and contingency. Let's turn now to the great mysteries that remain, the frontiers of current research where our understanding reaches its limits. Despite the remarkable progress we've made in understanding cosmic history, there are profound gaps in our knowledge, questions that current physics cannot answer. The most obvious mystery is dark matter. We know it exists. We can measure its gravitational effects. We know it makes up about 85% of all matter in the universe. But we don't know what it is. Is it a new type of fundamental particle? If so, what are its properties? Why hasn't it been detected directly despite decades of increasingly sensitive experiments? Could it be something more exotic, like primordial black holes formed in the early universe, or modifications to gravity that mimic dark matter's effects? The search for dark matter is one of the most active areas in physics. Deep underground detectors wait for dark matter particles to collide with atomic nuclei. Particle colliders try to produce dark matter in high-energy collisions. Telescopes search for indirect signatures of dark matter annihilation. Despite these efforts, dark matter remains elusive, its nature one of the deepest mysteries in cosmology. Even more mysterious is dark energy. We know the expansion of the universe is accelerating. We've measured this acceleration through observations of distant supernovae, the cosmic microwave background, and large-scale structure. We know that something with negative pressure, called dark energy, must fill space to cause this acceleration, but we don't know what it is. The simplest explanation is that dark energy is the cosmological constant, a property of space itself, vacuum energy that exerts negative pressure. But this raises a profound puzzle. When we calculate what the vacuum energy should be based on quantum field theory, we get an answer that's wrong by a factor of 10 to the power of 120, possibly the worst prediction in the history of physics. Why is the actual value so much smaller than quantum theory predicts? This is the cosmological constant problem, and it's deeply unsolved. Alternative explanations for dark energy involve new fields or modifications to general relativity on cosmological scales. Perhaps dark energy isn't constant but changes over time. Perhaps it's a new type of field called quintessence that varies in space and time. Perhaps gravity itself behaves differently on the largest scales than Einstein's theory predicts. These possibilities are being actively explored through observations and theory. Then there's the question of inflation itself. Did it really happen? The evidence is strong. Inflation explains the flatness of space, the uniformity of the cosmic microwave background, the origin of structure-forming fluctuations. But we don't have direct proof. We haven't detected the gravitational waves that inflation should produce, which would appear as B-mode polarization patterns in the CMB. Several experiments are searching for this signature, but so far, it hasn't been found. And if inflation did happen, what caused it? What field drove inflation? Why did it start? Why did it stop? How long did it last? What happened before inflation? These questions push physics to its limits. They require understanding quantum gravity, the unification of quantum mechanics and general relativity, which remains one of the greatest challenges in theoretical physics. As you lie here in the darkness, consider that our understanding of the universe's first moments requires physics we don't fully possess. We need quantum gravity to understand the Planck epoch. We need to understand the nature of dark matter and dark energy. We need to know whether inflation occurred and what caused it. These gaps in our knowledge are not failures, but invitations, frontiers calling to future generations of physicists and astronomers. Yet despite these mysteries, what we do understand is remarkable. We can trace cosmic history from fractions of a second after the Big Bang to the present day. We can explain the origin of elements, the formation of structures, the evolution of galaxies. We can predict the properties of the cosmic microwave background and have those predictions confirmed by observations. We can run computer simulations that reproduce the cosmic web. We can look back in time by observing distant objects and watch cosmic evolution in action. This understanding has been built over generations through the efforts of countless scientists. From Einstein's general relativity providing the framework for understanding cosmic expansion, to Hubble's observations revealing that expansion, to the theoretical predictions of Big Bang nucleosynthesis, to the discovery of the cosmic microwave background, to the detailed mapping of that background by satellite missions, to the discovery of dark energy through supernova observations, to the recent images from JWST showing the earliest galaxies. Each discovery built on previous work, each observation refined our understanding, each generation pushing the boundaries of knowledge a bit further. And this understanding changes how we see ourselves and our place in the cosmos. We are not separate from the universe, observing it from outside. We are part of it, products of its evolution, made of atoms forged in stars that formed from gas clouds that condensed from fluctuations created during inflation. Our existence is intimately connected to the universe's history. The carbon in your cells was created in the cores of stars through nuclear fusion. The oxygen you breathe was produced when massive stars exploded as supernovae. The calcium in your bones, the iron in your blood, all the heavy elements in your body were created in stellar furnaces and scattered through space to eventually be incorporated into the gas cloud that formed our solar system. You are made of stardust in a very literal sense. But it goes deeper. The atoms that make you were created from protons and neutrons that have existed since the first microsecond of the universe. These protons have been stable for over 13 billion years, surviving unchanged through the cosmic dark ages, the formation of the first stars, generations of stellar evolution, the formation of the solar system, the entire history of Earth and life. The very matter you're made of has memories stretching back to the beginning. And the pattern of your existence, the fact that you live in a galaxy, in a cluster, in a particular location in the cosmic web, traces back to the initial fluctuations from inflation. Your existence here and now is part of the story that began in the first moments of time. This perspective can be humbling and awe-inspiring simultaneously. We're tiny, fragile beings on a small planet orbiting an ordinary star in an unremarkable galaxy among billions. The universe is vast beyond comprehension, ancient beyond imagining. Yet we can understand it. We can trace its history, explain its evolution, predict its future. We can take a handful of fundamental laws and initial conditions, and from them derive the entire cosmic story. This ability to understand is itself remarkable and mysterious. Why should the universe be comprehensible to beings like us? Why should the mathematics we develop in our minds correspond to the workings of nature? Why should experiments performed in laboratories on Earth reveal laws that govern the evolution of galaxies billions of light years away? These are deep questions about the relationship between mind and cosmos, between consciousness and physical law. Perhaps the most profound legacy of the first moments is that they made understanding possible. The universe could have been chaotic, lawless, unpredictable, but it's not. It follows consistent rules, mathematical laws that hold throughout space and time. This regularity, this order, allows science to function. It allows us to make predictions, test theories, build understanding. And this order was established in those first moments, when the fundamental forces separated, when the laws of physics took their current form, when the initial conditions were set. As sleep draws near, reflect on the journey we've taken together. We've traveled from the Planck epoch, beyond which we cannot currently see, through the first picosecond when forces separated and inflation transformed the universe. We've witnessed the quark-gluon plasma and the confinement of quarks into protons and neutrons. We've seen Big Bang nucleosynthesis forge the light elements and recombination make the universe transparent. We've watched the Dark Ages give way to cosmic dawn as the first stars lit up. We've traced Ryanization and the hierarchical assembly of structure into the cosmic web we observe today. Each epoch built on the previous one. Each left its mark on what followed. The universe we inhabit today is the product of this long chain of cosmic evolution, stretching back to those first inconceivably brief moments when everything was decided. And now you exist, a conscious observer, capable of understanding this story. You can look at the night sky and see not just points of light, but galaxies billions of years old, structures formed through cosmic evolution that you can comprehend. You can look at a diagram of the cosmic microwave background and see in its patterns the seeds from which all structure grew. You can hold in your mind the entire sweep of cosmic history, from the Big Bang to the present, a story spanning 13.8 billion years compressed into understanding. This is the ultimate legacy of the first moments, not just the physical universe they created, but the universe's capacity to give rise to beings who can understand their own origins, who can trace their lineage back to the beginning, who can hold in consciousness the story of creation itself. We don't know if consciousness exists elsewhere in the cosmos. We haven't found definitive evidence of life beyond Earth. But we know it exists here, a product of cosmic evolution, matter arranged in patterns complex enough to reflect on its own existence and history. And this consciousness, this ability to understand, connects us across the vast gulf of time to those first moments when everything began.